Let go of everything you think you know about how the world works, because none of it applies here. Not the solid ground beneath your feet, not the steady tick of time, not the simple certainty that a thing is either here or there, or that you cannot be in two places at once. Quantum mechanics is the physics of the impossible made possible, and it begins with a single strange truth. The universe, at its smallest scale, does not behave like anything you have ever touched or seen or held in your hands. It behaves like a dream that follows its own logic and shifts the moment you try to pin it down. Think of a single particle of light or a single electron spinning in the dark. That particle does not travel from one point to another in a straight line, the way a ball travels through the air. It travels as a wave of pure probability, a spread-out whisper of maybe here and maybe there, and maybe everywhere in between, and only when you look does that whisper collapse into a single definite place, as if the universe was waiting all along for you to ask. This is not philosophy, and it is not poetry. This is the most rigorously tested science in human history, and it has never failed a single experiment. The strange part is that it works perfectly, even though it makes no sense at all, and that is the first thing you must accept before we go any further. You do not need to understand quantum mechanics with your thinking mind tonight. You only need to let it wash over you like slow water, because the mathematics is deep, and the ideas are vast, but the rhythm of it can carry you somewhere quiet. So settle into your bed, and feel the weight of your body sinking, and know that every atom beneath your skin is already obeying these quantum laws without effort or worry. The electrons in your bones are dancing their wave dances. The photons in the room are brushing against your eyelids, and none of it requires you to do a single thing except breathe and listen and let the strange, beautiful unreality of it all pull you gently towards sleep. That sounds strange, and it is strange. But it has been strange for as long as human beings have had the instruments to look closely enough to notice. The people who first noticed these things did not set out to make the world feel unfamiliar. They were trying to solve problems that seemed ordinary at the time. A hot piece of metal, a beam of light, the way a gas glows when you pass electricity through it. These were the kinds of questions that occupied physicists in the late 1800s. And they approached them with the same confidence a carpenter brings to a familiar workshop. They believed they understood the basic shape of the physical world. They believed the remaining work was about filling in details, not rebuilding the foundation. They were wrong, but they were wrong in a way that took decades to fully reveal itself. The story of how they were wrong, and what they found instead, is not a story you need to follow step by step. It is a story that has been told many times, in many ways, and the shape of it is what matters, not the dates or the names or the formulas. You can let the details drift past you like clouds. The important thing is that a group of people, working over several generations, began to notice that the rules they had written down for how the world works did not quite work at very small scales. Those rules were beautiful. They were elegant. They predicted planets and pendulums and the path of a cannonball with extraordinary accuracy. But when you applied them to the behavior of a single atom or a single particle of light, they failed. They failed so thoroughly that they predicted things that clearly did not happen, like the impossible glow of an ordinary object at ordinary temperatures. The person who first found a way out of that particular failure was not trying to start a revolution. He was trying to fix a glitch, to adjust an equation until the numbers came out right, the way you might adjust a clock that runs a little fast. He did not believe, at first, that the adjustment he made corresponded to anything real. It was a convenience, a mathematical trick, a way of getting the calculations to match the measurements, but the adjustment worked too well to ignore. And over the next several decades, other people, working on other problems, kept arriving at the same strange conclusion from different directions. They kept finding that the smooth, continuous, flowing world of classical physics was not the world that actually existed at the smallest scales. What existed instead was a world of steps, of jumps, of discrete chunks that could not be divided any further. They called those chunks quanta, from a Latin word meaning how much, and the name stuck because it described exactly what they were finding. There was a how much to everything. You could not have a little bit of this kind of energy. You could have one chunk, or two, or three, but never 1.5. The universe, at its smallest level, came in countable pieces. That is the first thing worth holding on to tonight. The world you experience is smooth. The light from a lamp brightens gradually. The sound of a voice fades gradually. The water in a glass warms gradually. But underneath that smoothness, at a scale you cannot see, the world is digital. It is made of steps. It is more like a staircase than a ramp, more like a ladder than a hill. And that staircase is not a metaphor either. It is a description of how energy itself behaves, and how matter behaves, and how light behaves. Everything you can see and touch is built from these steps, stacked so tightly together that they feel continuous, the way a movie feels continuous even though it is made of still images changing 24 times a second. If you let that sink in, you might start to feel the difference between the world as it appears and the world as it is. The bed beneath you feels solid. It feels like a single thing, a continuous surface holding you up. But what you are actually resting on is a vast collection of vibrating particles, each one separated from its neighbors by distances that are enormous compared to their own size. They do not touch. They never touch. What you experience as contact, as pressure, as solidity, is the electrical repulsion between the electrons in your body and the electrons in the bed, pushing against each other with a force that feels like a surface, because your nerves are wired to interpret it that way. If your nerves were wired differently, if they could feel the empty space instead of the force, the bed would feel like a scaffold, mostly gaps, mostly nothing, with tiny points of pressure scattered across it like stars in a dark sky. That is not a secret. That is not hidden knowledge reserved for experts. It is a plain fact of how things are built, and it has been a plain fact for over a century. The people who study these things have known about the staircase nature of reality since before your grandparents were born. They have built devices that depend on it, that use it, that rely on the fact that energy comes in chunks and not in a smooth flow. Those devices are in your room right now, probably within reach of your hand, doing their quiet work without needing you to understand how they do it. They work because the physics is reliable. The steps are dependable. The chunks are always the same size for the same type of energy, and that regularity, that absolute consistency, is what makes modern technology possible. If the world were not built from these discrete steps, if energy could flow in any amount at all, many of the devices you take for granted would simply not function. So you are lying in a room filled with proof of this staircase world, surrounded by evidence of it, breathing air that is mostly empty space, held together by forces that have no physical substance. That is the first layer of what people call quantum mechanics, though you do not need to use that phrase if it feels foreign. You can just call it the world as it actually is, as opposed to the world as it appears. And the difference between those two worlds is not a difference in kind, it is a difference in scale. The world as it appears is what you get when you step back far enough that the individual steps blur together into a smooth slope. The world as it actually is what you get when you lean in close enough to see each step individually, to count them, to notice that there is no such thing as standing between two steps. You are on one or you are on another. That is a hard thing to hold in your mind, because your mind is built for the large-scale world. Your senses evolved to track predators and find food, and navigate through forests and fields, not to perceive the internal structure of an atom. Your brain is a tool for survival, not a tool for fundamental physics, and it processes the world in a way that is useful for survival. It ignores the gaps between atoms because the gaps do not matter to a creature your size. It treats surfaces as continuous because continuous surfaces are what you need to sit on and walk on and build shelter against. The fact that surfaces are not actually continuous, that they are collections of particles held apart by invisible forces, is irrelevant to most of what you do in a day. It only becomes relevant when you ask the kinds of questions that physicists ask, questions about the nature of light and matter and the structure of the periodic table. But even if you never ask those questions, even if you never think about atoms or forces, or the empty space between your body and the bed, the truth of those things is still there. It is still happening. The particles are still vibrating. The forces are still pushing. The steps are still steps. You do not need to believe in them for them to be true. They are not a matter of opinion. They are a matter of measurement. And the measurements have been made, over and over, by people who did not want to believe what they were seeing. They did not want to replace a smooth, elegant world with a choppy, step-like one. But the evidence was too strong to ignore, and eventually, generation by generation, the smooth picture gave way to the step picture, not because anyone wanted it to, but because the universe kept showing the same pattern every time they looked. So let yourself rest in that. Let the ideas settle without trying to hold them tightly. You do not need to remember the term blackbody radiation, or the ultraviolet catastrophe, or any of the other phrases that might drift through your mind as you lie here. Those are labels for moments in the story, useful for reference but not essential for the feeling of the story itself. What is essential is the simple shape of it. The world is not what it appears to be. It is stranger than it appears. It is more divided, more discrete, more like a collection of tiny pieces than a continuous whole. And that strangeness is not located somewhere far away, in a laboratory or a textbook or a lecture hall. It is located right here, in the space between your skin and the sheets, in the air you are breathing, in the light that might be glowing faintly from a device on the nightstand. It is happening to you right now, as it always has, as it always will, without requiring your attention or your agreement. That might feel unsettling at first, the idea that the ground beneath you is not as solid as it seems. But it can also feel calming, if you let it. The solidity was never the point. The continuity was never the point. What matters is that the forces hold. The bed supports you, the air sustains you, the room keeps out the weather. The fact that these things are made of stepping stones rather than a smooth surface does not make them less reliable. If anything, it makes them more reliable, because the steps are fixed and unchanging. A chunk of energy is always the same size. A step is always the same height. There is no slippage, no gradual fading, no slow drift from one state to another. The universe, at its smallest scale, is exact. It is precise. It is consistent in a way that the smooth world of everyday experience never quite is. And that consistency is worth holding on to as you let your breathing slow and your muscles relax. The particles in this room are doing exactly what they are supposed to do. They are following the rules that were written into the fabric of things long before there were people to notice them. They do not need your help. They do not need your vigilance. They will keep doing what they do, whether you are awake or asleep, whether you are thinking about them or dreaming about something else entirely. You are not responsible for holding the atoms together. You are not responsible for maintaining the forces that keep your body from sinking through the bed. Those forces are automatic, impersonal, older than life on this planet, and they will continue long after you have stopped noticing them for the night. So let your shoulders drop, let your jaw unclench, let the weight of your body settle into the surface beneath you, trusting that the surface will hold, because the forces that hold it together have never failed, not once, in the entire history of the universe. The steps are stable, the chunks are consistent. The empty space between atoms is not a danger but a feature, built into the design of things, as ordinary as the space between one breath and the next. You are surrounded by a world that is strange and exact, and older than you can imagine, and it is holding you gently, without effort, without thought, the way it has held everything that has ever rested on its surface. Rest now, the rest of the night is yours. Before the steps were steps, before anyone had any reason to suspect the world was built from discrete pieces rather than continuous flow, there was a sense of completion. Physicists in the final years of the 1800s looked at their field and saw something close to finished. They had equations for motion that worked for planets and pendulums and projectiles. They had equations for electricity and magnetism that worked for wires and compass needles and the glow of a lamp. They had equations for heat that worked for engines and steam and the slow cooling of a cup of tea. It seemed like the major work was done, and what remained was measurement, refinement, the filling in of decimal places rather than the discovery of new continents. They did not say this out loud very often, because scientists tend to be cautious about declaring victory. But the feeling was there, underneath the daily work, a quiet confidence that the shape of physics was known. That confidence was not unreasonable. The framework they had built over the previous 2 centuries was genuinely powerful. Newton's laws described the motion of everything from a falling apple to the orbit of Jupiter with an accuracy that was almost unsettling. Maxwell's equations, written down in the 1860s, unified electricity and magnetism into a single set of rules and showed that light itself was a ripple in the electromagnetic field, a wave traveling through space at a fixed speed, carrying energy from one place to another. Thermodynamics, the study of heat and work, had reached a mature form that explained why engines run and why ice melts and why you cannot get more work out of a system than you put into it. The pieces fit together. They formed a coherent picture of a mechanical universe, a universe of cause and effect, of smooth motion and continuous change, a universe that obeyed laws that were elegant and comprehensible, and above all, universal. And yet, there were cracks. There were always cracks, if you knew where to look. Most of them were small enough to ignore, discrepancies in the data that could be blamed on measurement error or imperfect equipment. But some of them were too large to overlook, too persistent to explain away. One of those persistent cracks involved the way hot objects glow. It was a question so ordinary that it barely seemed like a question at all. You put a piece of metal in a fire, and it changes color. Dull red, then bright red, then orange, then yellow, then white if it gets hot enough. Everybody knew this happened. It was part of everyday experience, as familiar as the sound of a kettle boiling or the feeling of sunlight on your skin. But when physicists tried to predict exactly how much light of each color a hot object would emit, using the equations they trusted for everything else, they got nonsense. The nonsense was not subtle. It was not a small error that could be fixed with a slight adjustment. It was catastrophic, in the literal sense. The equations predicted that a hot object should radiate infinite energy at the highest frequencies of light. Not a lot of energy, infinite. An oven, according to the math, should not just warm the room. It should obliterate everything in its vicinity in a burst of ultraviolet radiation. The room should vanish. The building should vanish. The entire city should vanish if the oven stayed hot for more than a fraction of a second. This was obviously not what happened. Ovens sat in kitchens and laboratories and factories, glowing safely, radiating warmth and light, but not annihilating their surroundings. The equations were perfectly clear, the world was perfectly clear, and the two were in direct contradiction. This contradiction had a name. Physicists called it the ultraviolet catastrophe, because the problem was most severe at ultraviolet frequencies and because the situation was, in the grim humor of the time, catastrophic for the classical theory. It was a name that acknowledged the seriousness of the failure without offering any solution. The catastrophe sat there, unresolved, for years. It was not the only unresolved problem in physics at the time, but it was one of the most irritating, because it involved something so simple, a hot piece of metal, a spectrum of colors, the most basic measurement you could make. And yet the best minds of the era could not explain it. They could measure it perfectly. They could not derive it from their beloved equations. The person who eventually found a way out of this dead end was a man named Max Planck, a physicist working in Berlin. Planck was not a revolutionary. He was a conservative by temperament, someone who valued the classical framework deeply and wanted to preserve it. He did not want to overturn physics. He wanted to rescue it. He wanted to find a tweak, a patch, a small adjustment that would make the ultraviolet catastrophe disappear without disturbing the rest of the structure. He spent months working on the problem, trying various approaches, adjusting parameters, looking for a way to force the equations to match the measurements. Nothing worked until he tried something that seemed almost like a cheat. What he did was introduce a constraint. He said, in effect, that energy could not be emitted continuously, in any amount you please, the way water flows from a tap. Instead, energy could only be emitted in specific amounts, fixed packets, chunks that could not be subdivided. These packets had a size that depended on the frequency of the light. Higher frequency light, toward the ultraviolet end of the spectrum, could only be emitted in larger packets, and because it took a significant amount of energy to produce even a single packet of high-frequency light, hot objects almost never managed to do it. The high-frequency radiation that the old equations said should be produced in infinite quantities simply never materialized, because producing even one chunk of it required more energy than the system could spare. The catastrophe vanished. The math behaved. The measurements and the predictions finally agreed with each other. Planck called these packets quanta, a Latin word meaning how much, because they were fundamentally about quantity. You could have one quantum of energy at a given frequency, or two, or three, but never 1.5. The energy came in whole numbers, countable pieces, like eggs in a carton or rungs on a ladder. This was a strange idea, and Planck himself did not fully believe it at first. He treated it as a mathematical convenience, a way of making the numbers work, not as a description of how the world actually operated. He assumed that someone, eventually, would find a more classical explanation underneath the quanta, a smoother theory that would restore the continuous flow of energy he was more comfortable with. That explanation never materialized. The quanta kept appearing, in more and more contexts, and eventually it became clear that they were not a temporary patch. They were a permanent feature of the landscape. What Planck had done was introduce a constant into physics, a number that would come to be known as Planck's constant. It is a very small number, so small that it has no effect on the scale of everyday life. You will never notice Planck's constant in a swinging pendulum, or a rolling ball, or a boiling kettle. The packets of energy at ordinary temperatures and frequencies are so tiny that they blur together into a smooth flow, the way individual frames of a movie blur together into continuous motion. You only notice the chunks when you look at very small scales, the scales of atoms and particles, where the steps become visible and the smoothness breaks down. But the constant is always there, built into the fabric of things, a reminder that the world is not a continuous river, but a staircase. The existence of this constant was the first hint of the deeper structure that would later be called quantum mechanics. It was not a full theory. It was not even close. It was a single number, a single constraint, inserted into a single equation to solve a single problem. But it opened a door. It suggested that the universe, at its most fundamental level, did not work the way everyone had assumed. It suggested that smoothness was an illusion, a large-scale approximation of a choppy, discrete reality. It suggested that the continuous flow of energy was something the universe did at our scale, but not at its own. That is worth letting settle, because it is a genuine shift in how you think about the world. If energy comes in chunks, then the things energy builds must also come in chunks. Atoms, particles, light, everything eventually is made of countable pieces. The universe is not a single continuous substance, but a collection of individual units, each one distinct from the others, each one distinct from the others, each one obeying rules about how many can exist and how they can combine. That is a different picture from the smooth, flowing picture of classical physics. It is a picture of discrete islands in a sea of empty space, holding together not because they flow into each other, but because they form structures, like bricks in a wall or notes in a melody. You are made of those chunks. Every cell in your body is a collection of molecules. Each molecule a collection of atoms, each atom a collection of particles that obey the quantum rules. The food you ate today was built from those chunks. The air you are breathing is full of them. The bed beneath you is a vast assembly of them, held together by forces that operate at the level of the chunks, not at the level of the smooth surface you feel. The smoothness is real in the sense that your senses experience it, but it is not fundamental. It is an overlay, a way of organizing the chunks into a manageable pattern. Underneath the pattern, the chunks remain. This is the starting point for everything that follows. A single number, introduced reluctantly by a conservative physicist who wanted to save the old picture. A number that suggested energy came in pieces. A number that would eventually lead to a complete restructuring of how physics works. And a number that sits, tonight, in the equations that describe every light bulb, and every transistor, and every star in the sky. Planck's constant is not a theory. It is a fact, as well established as the fact that the Earth orbits the Sun. It has been measured in countless experiments, in countless ways, and every measurement agrees on its value. It is one of the bedrock constants of the universe, as fixed as the speed of light or the charge of an electron. So if you are lying there in the dark, feeling the weight of your own body against the mattress, you can know that the chunks are holding you up. The discrete pieces of the world are doing their job, pushing and pulling in exactly the way they are supposed to, creating the illusion of solidity, the illusion of continuity, the illusion of a smooth and stable world. The chunks are not a problem, they are not a flaw, they are the actual design, and they have been the actual design for as long as there has been a universe to have a design. The smoothness is what you get when you step back far enough to see the pattern rather than the pieces. The smoothness is the forest, the chunks are the trees, and both are real, just at different scales. Let that be enough for now. You do not need to remember the name Planck, or the constant he introduced, or the year he introduced it. You do not need to carry any of those details forward with you. What matters is the shape of the idea, the simple fact that the world is made of countable pieces, that the pieces are reliable, that they follow rules that have never been known to fail. The pieces are not going anywhere. They were here before you were born. They will be here after you are gone. They are doing what they do, right now, in the space between your body and the sheets, in the air moving in and out of your lungs, in the quiet hum of the room around you. Rest in that. Rest in the knowledge that the structure is sound, that the chunks are stable, that the forces that hold them together have held for billions of years and will hold for billions more. There is nothing you need to do. There is nothing you need to fix. The universe is handling itself, as it always has, and you are free to let go and drift into the dark. Let your attention drift back to that hot oven for a moment, the one that should have glowed with infinite energy but did not. The solution Planck found, the one that introduced the idea of energy packets, was a mathematical trick that worked. It made the numbers behave. It got rid of the nonsense prediction, but it did not answer the deeper question it raised. If energy really does come in these discrete chunks, these quanta, then what does that mean for light itself? Is light a continuous wave, as Maxwell had so elegantly shown, or is it a stream of these quanta, these tiny packets, arriving one after another? The answer, as it turned out, was both. And that both, that coexistence of two apparently opposite descriptions, became one of the central puzzles of the new physics. The person who pushed the puzzle forward was a young man working in a patent office in Bern, Switzerland. Albert Einstein was 26 years old in 1905, a clerk who spent his days examining applications for patents on electromagnetic devices, and his evenings thinking about the nature of light and matter. He had a job that gave him time to think, and he used that time well. That year, he published 4 papers that changed physics. One of them was on the special theory of relativity. One was on the equivalence of mass and energy, the equation that would become famous. One was on the random motion of particles in a fluid, and one was on the photoelectric effect, the phenomenon where light striking a metal surface releases electrons. The photoelectric effect was not a new thing. Physicists had known about it for years. They had observed it in laboratories. They had measured it. They knew that certain metals, when exposed to light of the right color, emitted electrons. They also knew that there were patterns to this behavior that did not fit the classical wave picture of light. The puzzle was this. If you shine dim light on a metal surface, you get few electrons. If you shine bright light of the same color, you get more electrons. But the electrons that come out, whether from dim light or bright light, have the same energy. They are not more energetic when the light is brighter. They are simply more numerous. And if the light is below a certain color, a certain frequency, no electrons come out at all, no matter how bright the light is. You can shine a floodlight on the metal, and nothing happens. You can shine a dim laser of a higher frequency, and electrons pour out. Under the classical wave picture, this made no sense. A wave's energy depends on its amplitude, its brightness. A bright wave carries more energy than a dim wave, so a bright wave should be able to knock electrons loose with more force, giving them more energy. And a dim wave of any frequency should eventually, if you wait long enough, deposit enough energy to release an electron. But that is not what happens. The color or frequency of the light determines whether electrons come out at all. The brightness determines only how many. The classical picture could not explain this. The classical picture was wrong. Einstein, reading about this problem, remembered Planck's quanta. He asked himself a bold question. What if light itself is made of quanta? What if the light beam is not a continuous wave, but a stream of individual particles of energy, each one carrying an amount of energy determined by its frequency? Each particle, which would later be called a photon, is a discrete unit. It either has enough energy to knock an electron loose from the metal surface, or it does not. If the photon's energy is too low, no amount of extra photons, no amount of brightness will make any difference. One low-energy photon hits one electron, and if it does not have enough energy, the electron stays put. A high-energy photon hits an electron, and the electron is released, carrying away the leftover energy. Brighter light means more photons, which means more electrons. Dimmer light means fewer photons, which means fewer electrons. But the energy of each individual electron depends only on the energy of the individual photon that knocked it loose, which depends only on the frequency of the light. The wave picture said brightness mattered. The particle picture, with Einstein's photons, said frequency mattered. The experiments said frequency mattered. Einstein was right. This was a radical claim. Einstein was saying that light, which Maxwell had shown beyond any doubt to be a wave, could also be described as a stream of particles. He was not saying light was not a wave. He was saying light was also a particle, depending on how you looked at it. The wave description worked for some experiments, the ones where light spread out and interfered with itself. The particle description worked for others, the ones where light interacted with matter in discrete, countable ways. Both descriptions were necessary, both were accurate, neither could replace the other. It was this paper, the one on the photoelectric effect, that later earned Einstein his Nobel Prize. Not relativity, not the equation that made him famous. The paper that said, light comes in chunks. The physics community, conservative as it was, recognized that this was a genuine advance, a real insight into the nature of reality. They gave him the prize not for overturning the old physics but for extending it, for showing that the quanta Planck had introduced as a mathematical convenience were actually out there in the world, doing real work. Einstein had taken Planck's reluctant step and made it bold. He had said plainly that nature is quantized. Light is quantized. Energy is quantized. The chunks are not a trick. They are the truth. But this created a tension that would define the next several decades of physics. Maxwell had shown light is a wave. Einstein had shown light is a particle. Both were correct. Both were supported by evidence. And yet they seem to contradict each other at a fundamental level. A wave is spread out. It occupies a region of space. It has peaks and troughs. It bends around corners. It overlaps with itself to create interference patterns. A particle is localized. It has a definite position at any given moment. It travels along a path. It does not interfere with itself. It arrives in one place at a time. The same thing cannot be both spread out and localized. The same thing cannot both interfere with itself and travel in a straight line. And yet light did both, depending on the experiment. This was not a problem that could be ignored. It was not a minor technicality. It was a direct challenge to the way physics had always worked, the way it had always described objects. An object was either a wave or a particle. It could not be both, but light was both. And if light was both, then perhaps other things were both as well. Perhaps matter itself, which everyone had always treated as particles, could also behave as waves. Perhaps the wave-particle duality, the coexistence of two contradictory descriptions, was not a quirk of light, but a feature of everything. That thought took a while to develop. The physics community did not immediately embrace Einstein's photons. Many resisted the idea. They preferred the wave picture. It was elegant, continuous, comfortable. The particle picture seemed crude, lumpy, almost primitive. But the evidence kept accumulating. The photoelectric effect was real. The photons were real. And eventually, the community had to accept that light had two faces, two natures, two ways of being described, neither of which was complete on its own. This duality, this split personality of light, became one of the foundational ideas of quantum mechanics. It was not a flaw, it was a clue. It suggested that the old way of thinking about the world, the way that assigned a single definite nature to every object, was insufficient. It suggested that the world was more flexible, more fluid, more strange than anyone had imagined. An object could be a wave for one purpose and a particle for another. It could be both, without contradiction, because the contradiction was in the description, not in the thing itself. The thing itself was not a wave or a particle. It was something else, something that could appear as a wave in some contexts and as a particle in others, depending on how you chose to look at it. That is a difficult idea to hold on to. It is not intuitive. It does not match the way we experience the world. You do not see your hand as both a wave and a particle. You see it as a solid object, definite and localized, moving through space on a clear trajectory. But at the scale of atoms and photons, the rules are different. The rules allow for this flexibility, this duality. The rules are not broken, they are just different. And part of the work of quantum physics, the work that would come in the years following Einstein's paper, was to understand those rules, to write them down, to make them precise enough to predict what would happen in any experiment. Einstein himself, for all his boldness in proposing the photon, was never entirely comfortable with the direction this work would take. He was a realist. He believed in an objective world, a world that existed whether you were looking at it or not. He believed that the job of physics was to describe that world accurately, not to give up on describing it because the descriptions got strange. He would later become one of the sharpest critics of the more radical interpretations of quantum mechanics, the ones that seemed to say the world depended on observation, that there was no reality until you measured it. He famously said that God does not play dice, meaning that the universe is not random, not probabilistic, not a matter of chance. He wanted a clean, deterministic picture, a picture where every particle had a definite position and momentum at all times, even if we could not know them. That desire, that hope, would eventually be frustrated by the very theory he had helped create. But that frustration was still years away. In 1905, Einstein was a young patent clerk making a radical proposal about the nature of light. He was not thinking about the philosophical implications. He was thinking about experiments, about data, about making the numbers fit. He was thinking about the photoelectric effect. And he found an explanation that worked. That explanation, the photon, the particle of light, was a step into a new world, a world where the old certainties of classical physics began to dissolve and new patterns began to emerge. So as you lie there, with your eyes closed or open, with the dark settling around you, let the duality of light be something you hold loosely. Light is a wave, light is a particle. Both statements are true, both statements are incomplete. The reality is something that encompasses both, something that is more than either description alone can capture. That is not a failure of physics, it is a feature of the universe, a feature that tells you something deep about the nature of reality. Reality is not always simple, it is not always intuitive, it is not always easy to fit into the categories we have built for it. But it is always there, always reliable, always doing what it does, whether you understand it or not. And tonight, you do not need to understand it. You only need to let it be, to let it rest, to let the wave and the particle coexist in your awareness, without forcing them to choose one or the other. They do not need to choose. They are both true, they are both real, and they are both happening right now, in the light that might be filtering through the curtains, in the air around you, in the quiet dark of the room. Rest in that. Let the duality be. There is no need to resolve it tonight. While Einstein was working out the nature of light, showing that it came in discrete packets called photons, another line of inquiry was developing in a different direction, one that would eventually meet Einstein's work and merge with it to form the foundation of quantum mechanics. This other line involved the structure of atoms, the tiny building blocks of matter that had been suspected for centuries, but only recently confirmed to exist. By the early 1900s, physicists knew that atoms were real. They knew atoms were small, far too small to see, and they knew atoms had some kind of internal structure. What they did not know was what that structure looked like, how the pieces of an atom fit together, or why atoms were as stable as they seemed to be. The person who gave them the first clear picture of atomic structure was a New Zealand physicist named Ernest Rutherford. In 1911, working with his colleagues Hans Geiger and Ernest Marsden, Rutherford conducted an experiment that would change the way physicists thought about matter. They took a thin sheet of gold foil, only a few atoms thick, and fired a beam of positively charged particles at it. Most of the particles passed straight through the foil, as if the foil were not there at all. A few were deflected at small angles, and a very small number, about 1 in 8,000, bounced straight back, as if they had hit something solid. This was a genuinely strange result. If atoms were solid, continuous blobs of matter, the particles should have been stopped or scattered in all directions. If atoms were mostly empty space, with the positive charge spread out evenly through them, the particles should have passed through with only slight deflections. Rutherford's result suggested something different. It suggested that atoms were mostly empty space, with a tiny, dense, positively charged core at the center, and that this core, later called the nucleus, was what the particles were bouncing off when they came back the way they came. The gold foil was mostly empty space, so most particles passed through, but occasionally a particle would hit the nucleus head-on, and the concentrated positive charge would send it flying backward. This picture of the atom, with a tiny nucleus at the center and electrons somewhere around it, was a major advance. It replaced the earlier pudding model, which imagined the positive charge spread throughout the atom like batter, with electrons embedded in it like raisins. Rutherford's model was different. It was more like a solar system, with the nucleus as the sun and the electrons as planets orbiting around it. The electrons were held in place by electrical attraction, the same force that pulls opposite charges together and pushes like charges apart. The nucleus was positive, the electrons were negative, so the electrons naturally orbited the nucleus, the same way planets orbit the sun, because they were attracted to it and could not fall in. This was a tidy picture, but it had a fatal flaw. The same classical physics that had predicted the ultraviolet catastrophe for the hot oven predicted something equally impossible for Rutherford's atom. According to Maxwell's equations, an orbiting electron is a moving electric charge, and a moving electric charge radiates energy in the form of electromagnetic waves, which is another name for light. That means an orbiting electron should lose energy as it moves, slowly at first, then faster, spiraling inward toward the nucleus until it crashes into it. The calculation was straightforward. An electron orbiting a nucleus should lose enough energy to spiral inward and collide with the nucleus in less than a trillionth of a second. Every atom in the universe should have collapsed long ago. Every solid object should have disintegrated. Every cell in your body should have ceased to exist. The fact that you were still here, lying on this bed, breathing this air, was direct evidence that Rutherford's solar system picture was missing something essential. The classical laws did not work at the scale of the atom. Something else was going on. That something else turned out to be another application of the quantum rules that Planck and Einstein had introduced. The person who applied those rules to the atom was a Danish physicist named Niels Bohr, who came to Rutherford's laboratory in 1912 and started thinking about the stability problem. Bohr was young, in his late 20s, and he was deeply impressed by Rutherford's work. He saw the elegance of the solar system model, and he also saw its flaw. He understood that classical physics could not explain why the atom was stable. He also understood that the quantum ideas, the ideas of discrete packets and fixed amounts of energy, might provide the missing piece. Bohr's insight was this: what if the electrons in an atom could not occupy just any orbit, at any distance from the nucleus, the way a planet can orbit at any distance from the sun? What if only certain specific orbits were allowed, each one corresponding to a particular fixed amount of energy? These orbits were like rungs on a ladder. An electron could sit on one rung or another, but it could not sit in between. As long as it stayed on a rung, it did not radiate energy, did not spiral inward, did not crash into the nucleus. It simply stayed where it was, stable, quiet, doing nothing. The classical rules said it should radiate. The quantum rules, Bohr's rules, said it did not. The quantum rules matched what actually happened. Atoms were stable. Therefore, the quantum rules were correct. The allowed orbits, the rungs on Bohr's ladder, were determined by the quantum nature of energy. Each rung corresponded to a specific amount of energy, a specific distance from the nucleus. The higher the rung, the more energy the electron had, and the farther it was from the nucleus. The lower the rung, the less energy it had, and the closer it was. An electron could jump from a higher rung to a lower rung, releasing energy in the process. It could also jump from a lower rung to a higher rung, absorbing energy, but the jumps were not smooth. They were discrete, abrupt, instantaneous. An electron did not move gradually from one rung to the next. It simply vanished from one and appeared at the other, carrying the energy difference with it. This explains something that had puzzled physicists for decades. When you heat an element, it glows with a specific set of colors, a kind of spectral signature. Hydrogen glows with a particular pattern of lines. Helium glows with a different pattern. Every element has its own pattern, its own barcode. Under Bohr's model, this made perfect sense. The barcode lines corresponded to the jumps between rungs. An electron falling from the third rung to the second rung released a photon of a specific energy, which corresponded to a specific color of light. An electron falling from the fourth rung to the second rung released a different photon, with a different energy and a different color. Each line in the barcode was a specific jump, a specific electron moving from one rung to another and releasing a specific packet of light in the process. The set of allowed rungs and the set of allowed jumps between them determined the barcode. Hydrogen had one set of rungs, so it had one barcode. Helium had a different set, so it had a different barcode. The barcodes were not arbitrary. They were the fingerprints of the rungs. Bohr's model was a triumph. It matched the hydrogen barcode almost perfectly, an accuracy that was deeply satisfying to anyone who cared about the numbers. It showed that the quantum rules were not just a patch for a single problem. They were a general principle, a way of thinking about the world that applied to atoms as well as to light. It showed that the universe was built from discrete steps, from rungs, from quanta, and that these steps governed the behavior of matter at its most fundamental level. But Bohr's model had its limits. It worked beautifully for hydrogen, the simplest atom, with just one electron orbiting a single proton. It did not work nearly as well for helium, with two electrons. It failed completely for anything more complicated. The rungs were not derived from any deeper principle. They were just assumed, declared into existence, because they made the numbers fit. Bohr had built a ladder, but he could not explain why the ladder had the rungs it had, or why those rungs were spaced the way they were. He had found a pattern, but he had not found the pattern's source. This was the state of physics in the early 1920s. A collection of clues, a set of puzzles, a few partial solutions that worked for some cases and failed for others. Planck had quantized energy. Einstein had quantized light. Bohr had quantized the atom. But nobody had a unified theory, a single framework that explained all of it. The rungs were there, but the ladder was missing. The clues were real, but the story that connected them was incomplete. Bohr himself was aware of this. He knew his model was a patch, a stopgap, a way of making the numbers fit without fully understanding why. He spent years trying to develop a deeper theory, a more complete picture, but he never quite got there. The complete picture would come from other people, younger physicists, working with new mathematics and new ideas. But Bohr's contribution was essential. He had shown that the quantum rules applied to atoms, that the structure of matter itself was quantized. He had given physicists a starting point, a concrete problem to solve, a set of rungs that needed to be explained. As you lie there, letting the quiet settle around you, think about those rungs for a moment. Think about the ladder that Bohr built, the allowed orbits, the jumps between them, the packets of light that are emitted or absorbed in the process. That ladder is not a metaphor. It is a description of how atoms actually work, how they stay stable, how they glow with the colors they glow. Your own body is made of atoms, trillions of them, each one with its own set of rungs, its own allowed orbits, its own quantum structure. Those rungs are not a story that someone made up. They are a physical fact, as real as the bed beneath you, as real as the air in your lungs. They have been there all along, doing their quiet work, holding your atoms together, keeping you stable, keeping you whole. The rungs are not something you need to understand completely. You do not need to know the energy of each orbit, or the wavelength of each photon, or the mathematics that describes the jumps. You only need to know that they are there, that they are reliable, that they have been doing their work for billions of years and will continue to do their work for billions more. The rungs are not going anywhere. They are built into the fabric of the universe, as fixed and unchanging as the speed of light. And you are built from them, just as much as the stars are built from them, just as much as the air you are breathing is built from them. So let yourself rest in that. Let the rungs hold you, the way the rungs of a ladder hold someone climbing. Let the quantum structure of the atom be something you trust, something you let support you, something you do not need to question or analyze or fully grasp. The rungs are there, and they are stable, and they are doing their work. The electrons in your body are sitting on their rungs, not radiating, not collapsing, not spiraling into destruction. They are simply there, doing what they are supposed to do, following the rules that have been written into the universe since before there were humans to write them down. That is enough. That is more than enough. Rest in that, and let the quiet take over. The rungs were there, but the ladder was missing. That was the state of physics in the years after Bohr published his model of the atom. He had shown that electrons could only occupy certain orbits, certain fixed energy levels, and that they jumped between these levels in discrete steps, emitting or absorbing light in the process. It was an elegant picture. It matched the data for hydrogen. It explained the barcode lines that each element produced when heated. But it did not explain why these particular orbits were allowed, or why the electron did not radiate energy when it was sitting on a rung, or what an electron actually was when it was not being measured. The rules worked, but they were imposed from outside, assumed rather than derived. Physicists had the behavior, but they did not have the underlying cause. The person who took the first real step toward finding that cause was a French physicist named Louis de Broglie. De Broglie came from a wealthy aristocratic family, and he had the freedom to pursue whatever intellectual interests he chose. He chose physics, and he chose to think deeply about the nature of matter and light. In 1924, as part of his doctoral thesis, he proposed an idea that was both simple and radical. If light, which everyone had always treated as a wave, could also behave as a particle, then perhaps the reverse was also true. Perhaps particles, which everyone had always treated as tiny solid objects, could also behave as waves. Perhaps electrons were waves, not just in some abstract mathematical sense, but in a real physical sense. Perhaps the wave nature of matter was not an occasional quirk, but a fundamental property of everything. De Broglie did not pull this idea out of nowhere. He was building on the work of Einstein and Planck, on the idea that light had a dual nature, wave and particle. He was also drawing on the work of Bohr, on the idea that electrons had discrete energy levels. He asked himself what would happen if you treated an electron as a wave that was somehow confined to the space around the nucleus. The answer, he found, was that only certain wavelengths would fit. The electron wave circling the nucleus would have to close on itself smoothly, like a note on a guitar string, with no jagged mismatch where the ends met. Only specific wavelengths allowed that smooth closure. Those wavelengths corresponded to specific energies, which corresponded to the specific orbits that Bohr had assumed. The rungs were not arbitrary. They were the only wavelengths that could fit in the space around the nucleus. This was a profound insight. It meant that the quantization of atomic energy levels was not a strange rule imposed by some unknown force. It was a geometric necessity, a consequence of the wave nature of matter. If you accepted that electrons were waves, then the rungs fell out naturally. You did not need to assume them. You could derive them. De Broglie had found the reason behind Bohr's rules, the explanation for why the ladder had the rungs it had. The rungs were where the wave could fit. The idea was strange enough that de Broglie's thesis committee was uncertain what to make of it. They consulted Einstein, who recognized the importance of the idea immediately. Einstein wrote back, praising de Broglie's work and lending his considerable authority to the proposal. With Einstein's endorsement, the idea gained traction. De Broglie's wavelength, the wavelength associated with any moving particle, became a key concept in the new physics. It was a small number for everyday objects, so small that it had no observable effect. But for electrons, it was large enough to matter, large enough to shape their behavior, large enough to explain the structure of atoms. The idea that particles are also waves is one of the central ideas of quantum mechanics. It is called wave-particle duality, and it applies to everything, not just light and electrons. Every object, from a grain of sand to a planet, has a wavelength associated with it. For large objects, the wavelength is so tiny that it cannot be measured. It is smaller than the nucleus of an atom, far too small to affect the behavior of the object. That is why you never see the wave nature of a baseball or a car. The wave nature is there, mathematically, but it is completely swamped by the object's other properties. It has no observable effect. But for small objects, for electrons and atoms and molecules, the wavelength is large enough to be significant. It determines how they move, how they interact, how they organize themselves into the structures we see around us. De Broglie's idea was a bridge between the old physics and the new. It connected the wave nature of light, established by Maxwell, to the particle nature of matter, established by Newton and Rutherford. It showed that the two descriptions were not opposites but complements, two aspects of a single deeper reality. It also provided the missing piece that Bohr had needed. The rungs were not arbitrary. They were the only places where an electron wave could exist. This is worth letting settle, because it changes the way you think about matter. You are made of particles, but those particles are also waves. They are spread out, in some sense, occupying a region of space rather than a single point. They interfere with themselves, the way waves do. They have wavelengths, frequencies, phases. They are not tiny billiard balls, moving along definite paths. They are more like ripples, spreading out, overlapping, forming patterns. Those patterns are what give atoms their structure, molecules their shapes, matter its properties. The wave nature of matter is not a philosophical speculation, it is a physical fact, confirmed by experiments that have been repeated many times, in many ways, by many different people. The experiments that confirmed de Broglie's idea came soon after he proposed it. In 1927, two American physicists, Clinton Davison and Lester Germer, fired a beam of electrons at a crystal and observed that the electrons scattered in a pattern that could only be explained if they were waves. The pattern was exactly the kind of interference pattern that light produced when it passed through a grating. The electrons were interfering with themselves, the way waves do. It was a direct demonstration that electrons had a wavelength, that they were not just particles but also waves. The same year, a British physicist named George Paget Thomson performed a similar experiment and got the same result. Wave-particle duality was not a guess, it was a fact. So the electron, which Rutherford had pictured as a tiny planet orbiting a nucleus, turned out to be something else entirely. It was not a planet. It was not even a particle in the ordinary sense. It was a wave, spread out around the nucleus, existing in a state of superposition, occupying a range of positions rather than a single definite location. The orbits that Bohr had assumed were not orbits at all, in the planetary sense. They were wave patterns, standing waves, like the notes on a guitar string. The electron did not move along a path. It was a pattern, a vibration, a ripple in the field. And that pattern, that vibration, determined the energy of the atom. The idea that matter is made of waves is not easy to hold on to. It does not match your everyday experience. You do not see yourself as a wave. You see yourself as a solid object, with a definite location and a definite mass. But that solidity, that definiteness, is an illusion of scale. At the atomic level, the rules are different. The wave nature dominates. The solidity you feel is an emergent property, a consequence of many waves interacting, many particles combining, many patterns forming a larger pattern. The bed beneath you feels solid because the electron waves in the bed are interacting with the electron waves in your body, creating a force that pushes you up. That force is real, but it is not a contact force. It is a wave interaction, a quantum effect, happening at a scale you cannot see. De Broglie's insight that particles are waves was the key that unlocked the next stage of quantum mechanics. It gave physicists a new way to think about the atom, a way that did not require arbitrary assumptions. It also gave them a new way to think about everything else. If electrons were waves, then all matter was waves. The universe was not a collection of tiny billiard balls. It was a vast collection of ripples, spread out across space, overlapping and interfering, forming the structures we see around us. That is a different picture from the classical picture, a picture that takes some getting used to, but it is the picture that the evidence supports. As you lie there, with the dark settling around you, let the wave nature of matter be something you rest in. You are a wave, in a sense, spread out across the space of your body, occupying a range of positions rather than a single point. That is not something you need to feel or understand. It is just what you are, what everything is, at the deepest level. The wave nature does not make you less solid. It makes you more connected, more interwoven with the world around you. The waves in your body are interacting with the waves in the bed, the air, the room. You are not separate from your surroundings. You are part of them, part of the same vast field of ripples, the same great ocean of wave patterns that makes up the universe. Rest in that. Let the waves carry you, the way they have carried everything since the beginning of time. De Broglie had proposed that matter has a wave nature, and the experiments had confirmed it. Electrons, the tiny particles that orbit atomic nuclei, produced interference patterns, the hallmark of waves. They diffracted around obstacles. They spread out and overlapped with themselves. They behaved, in some contexts, exactly like light. This was a genuine shift in how physicists thought about the world, but it was still a qualitative shift, a broad idea without a precise mathematical form. What was needed was an equation, a set of rules that could describe these matter waves with the same precision that Maxwell's equations described light waves. What was needed was a theory that could take the wave nature of matter and turn it into a tool for calculation, a way of predicting the behavior of atoms and electrons with accuracy. That tool arrived in early 1926 in the form of an equation written down by an Austrian physicist named Erwin Schrödinger. Schrödinger was in his late 30s when he produced his equation, older than some of the other young physicists who were revolutionizing the field, but still young enough to be flexible in his thinking. He was working at the University of Zurich, and he had been following the developments in quantum theory with interest. He had read de Broglie's thesis, and he had been struck by the idea that electrons were waves. He began to wonder what kind of equation would describe such a wave, how it would evolve over time, how it would respond to forces. The answer he found was elegant, powerful, and extraordinarily useful. Schrödinger's equation, which now bears his name, is the central equation of quantum mechanics. It describes how the wave function of a particle changes over time. The wave function is a mathematical object that contains all the information about the particle, all the information that can be known. It is not a physical wave in the ordinary sense. It does not ripple through space the way a wave on a pond does, but it behaves mathematically like a wave, with peaks and troughs, with interference and diffraction, with all the properties that waves have, and from it, you can calculate everything you need to know about the particle. The equation is not something you need to understand in detail. It is enough to know what it does. It takes the forces acting on a particle, the environment it is in, and it produces a description of the particle's wave function, a description that tells you where the particle is likely to be, how fast it is likely to be moving, what energy it is likely to have. It is a predictive tool, a way of turning the abstract idea of matter waves into concrete numerical answers. And it works. It works for atoms, it works for molecules, it works for the behavior of electrons in solids, it works for the structure of the periodic table, it works for chemistry, it works for almost everything. When Schrödinger applied his equation to the hydrogen atom, something remarkable happened. The equation produced a set of allowed wave patterns, stable solutions that did not change over time. These wave patterns corresponded to the energy levels that Bohr had assumed. The rungs on Bohr's ladder emerged naturally from the mathematics. Schrödinger had not needed to assume them. They had fallen out of the equation as consequences. The ladder was no longer a patch. It was a derivation. The wave nature of the electron, combined with the forces acting on it, produced the discrete energy levels that Bohr had observed. The rungs were not arbitrary. They were a direct consequence of the wave nature of matter. This was a profound achievement. Schrödinger had given physicists a single equation that could, in principle, describe any quantum system. He had unified the patchwork of quantum rules into a coherent mathematical framework. He had shown that the strange behavior of atoms and electrons was not a collection of isolated oddities, but a single coherent phenomenon, governed by a single set of rules. The equation was not intuitive, it was not easy to visualize, but it was precise. It made predictions that could be tested, and those predictions matched the experimental results with an accuracy that was deeply reassuring. The Schrödinger equation is often described as the most important equation in all of quantum mechanics, and that is not an exaggeration. It is the foundation on which the rest of the theory is built. It is the tool that physicists use to calculate the behavior of atoms, molecules, solids, and all the other quantum systems that make up the physical world. It is the reason quantum mechanics can be applied to real problems, to the design of transistors and lasers and MRI machines. Without it, quantum mechanics would be a collection of qualitative ideas, a set of broad principles without the precision needed for practical use. With it, it became a working theory, a tool for understanding and manipulating the world at its smallest scales. But the equation did not answer every question. It told you how to calculate the wave function, but it did not tell you what the wave function meant. It told you how the wave function evolved, but it did not tell you what the wave function was. These questions, the interpretive questions, would become the source of intense debate in the years that followed. Physicists would argue about whether the wave function represented a real physical wave or a probability distribution. They would argue about whether the wave function collapsed upon measurement, and if so, how. They would argue about whether quantum mechanics was a complete theory or merely a useful approximation. These arguments were not resolved quickly, and some of them have never been fully resolved. But the equation itself was solid. It made correct predictions. It matched experiments. It gave physicists a way to do calculations that were accurate and reliable. That was enough for many of them. They did not need to know what the wave function meant. They only needed to know how to use it. The equation worked, and that was what mattered. Schrödinger himself was not entirely comfortable with the interpretation that would later become dominant. He had originally hoped that his wave function would represent a real physical wave, a genuine ripple in some underlying medium. He wanted a return to a more classical picture, a picture where the world was made of real things that existed whether you were looking at them or not. He was disappointed when other physicists, particularly Max Born, proposed a different interpretation, one that treated the wave function as a probability distribution rather than a physical wave. Born's interpretation, which became known as the Copenhagen interpretation after the city where Bohr worked, said that the wave function did not represent a real wave. It represented the probability of finding the particle in a particular location. The particle itself was not spread out, it was just likely to be found in some places and unlikely to be found in others. The wave was a wave of knowledge, not a wave of matter. Schrödinger disliked this interpretation. He wanted a real wave, a physical wave, a wave that existed in space. He spent years trying to develop a version of quantum mechanics that preserved the reality of the wave function, but he never succeeded. The probabilistic interpretation, despite its strangeness, proved to be the most useful. It matched the experiments. It made the right predictions. It became the standard way of understanding quantum mechanics, the way most physicists were taught to think about the wave function. The wave function did not represent a real wave. It represented a wave of possibility, a wave of what might happen, not what was happening. This distinction is important, and it is worth holding on to for a moment. If the wave function is a wave of probability, then the particle does not have a definite location until you measure it. It is spread out, in a sense, across all the locations where the wave function is non-zero. It is not that the particle is in one place and you do not know where. It is that the particle is not in any one place. It is in all of them, simultaneously, in a state of superposition. The wave function describes that superposition, that spread of possibilities. And when you measure the particle, when you interact with it in a way that forces it to choose a location, the superposition collapses into a single outcome. The particle appears in one place, and the wave function becomes concentrated there. This is a hard idea to accept. It goes against the way we normally think about the world. We are used to objects having definite properties. We are used to knowing where things are. The idea that an electron does not have a definite location until you measure it is strange. It is not intuitive. It does not match our experience. But it is what the mathematics says, and it is what the experiments confirm. The electron is not a tiny billiard ball. It is a wave of possibility, a spread of potential locations, until something forces it to choose. This is the heart of quantum mechanics. It is not a theory of what is. It is a theory of what might be, and what will be when you look. It is a theory of potential, of probability, of the strange connection between observation and reality. It is a theory that makes the observer part of the picture, not separate from it. That is a difficult role for observers to accept. We like to think we are outside the world we are observing, that our looking does not change what we are looking at, but quantum mechanics suggests otherwise. It suggests that looking, measuring, observing, forces the world to take a definite form. Before that, the world is indefinite, spread out, a wave of possibilities. Schrödinger himself never fully accepted this. He remained troubled by the probabilistic interpretation until the end of his life. He famously proposed the thought experiment with the cat, the one where a cat is sealed in a box with a radioactive atom and a poison mechanism, and the cat ends up neither alive nor dead until someone opens the box. He proposed it as a criticism of the probabilistic interpretation, a way of showing how absurd it would be to apply the rules of superposition to everyday objects. He did not think the cat was really both alive and dead. He thought the interpretation that led to that conclusion must be wrong. But the interpretation did not go away. It became the standard view, despite its strangeness, despite its counterintuitive nature, because it worked. The mathematics worked. The predictions worked. The experiments confirmed the predictions. The interpretation, however strange, was the one that fit the evidence. As you lie there, with your eyes closed or open, with the dark pressing in around you, let the wave function be something you rest in. It is not something you need to understand. It is not something you need to visualize. It is a mathematical description, a tool, a way of predicting what will happen in the quantum world. The quantum world is not the world you experience. It is the world underneath, the foundation, the structure that supports everything you see and touch. The wave function describes that world, in a language that is precise and abstract, and not easily translated into everyday terms. But it describes it accurately. It is the best description we have, and it has been tested, over and over, and it has never been found wanting. So let the wave function be. Let it do its work. Let the electrons in your body exist in their superpositions, spread out across the space of your atoms, doing what electrons do. They do not need you to understand them. They do not need you to believe in them. They are there, doing what they have always done, following the rules that Schrödinger wrote down nearly a century ago. Those rules are not going anywhere. They are built into the fabric of the universe, as fixed and reliable as the speed of light. And you are built from them, just as much as the stars are built from them, just as much as the air you are breathing is built from them. Rest in that. Let the wave function carry you, the way it has carried everything since the beginning of time. While Schrödinger was developing his wave equation, a very different approach to the same problems was being pursued by a young German physicist named Werner Heisenberg. Heisenberg was in his early 20s when he began his work, barely out of university, but he was already recognized as one of the most gifted theorists of his generation. He was working in Göttingen and then in Copenhagen, and he was deeply dissatisfied with the state of quantum theory. He found Bohr's model too ad hoc, too reliant on assumptions that had no clear justification. He wanted a theory that was grounded in observables, in the things that could actually be measured in an experiment, not in pictures of orbits and waves that could not be directly seen. Heisenberg's approach was different from Schrödinger's. Instead of starting with a wave and trying to describe its behavior, Heisenberg started with the measurements themselves. He focused on the quantities that could be observed, like the position of an electron or the amount of energy it carried. He then constructed a mathematical framework based on these observables, using a kind of mathematics called matrix mechanics. The framework was abstract, difficult to visualize, and far removed from the familiar world of waves and particles. But it produced the same results as Schrödinger's equation. The two approaches, wave mechanics and matrix mechanics, were mathematically equivalent. They were two different ways of expressing the same underlying theory. This equivalence was an important moment. It meant that quantum mechanics was not a collection of arbitrary rules. It was a coherent theory, capable of being expressed in multiple mathematical languages. The same predictions emerged from both approaches. The same calculations yielded the same answers. The theory was robust, consistent, and reliable. It could be used to solve problems in a variety of ways, depending on the preference of the physicist doing the solving. But Heisenberg contributed more than just an alternative mathematical framework. He also contributed one of the most famous and unsettling ideas in all of physics, the uncertainty principle. In 1927, working through the implications of his matrix mechanics, Heisenberg realized that there was a fundamental limit to how precisely certain pairs of properties could be known. The most famous pair is position and momentum, the location of a particle and how fast it is moving. Heisenberg showed that the more precisely you know one of these quantities, the less precisely you can know the other. If you pin down the position of an electron with great accuracy, its momentum becomes uncertain. If you pin down its momentum, its position becomes uncertain. It is not a matter of measurement error. It is a built-in feature of the quantum world. This is a genuinely hard idea to accept. It goes against the intuition that the world has definite properties, whether we measure them or not. We are used to thinking that an object has a definite position and a definite momentum, and that our measurements simply reveal what is already there. The uncertainty principle says that this is not true for quantum objects. They do not have both a definite position and a definite momentum simultaneously. Those properties are not both well defined at the same time. The world at its smallest scale is fuzzy. It is not a collection of sharp points and clear trajectories. It is a blur of possibilities, a spread of potential values, and the act of measuring one property forces the other to become less certain. The uncertainty principle is not a statement about human ignorance. It is not a limitation of our instruments. It is a statement about what the world is like. The world does not have sharp positions and sharp momentums. It has fuzzy positions and fuzzy momentums. The fuzziness is not a flaw. It is a feature. It is built into the fabric of reality. This idea was unsettling to many physicists, including Einstein. Einstein was a realist. He believed that the world had definite properties whether we observed them or not. He believed that the uncertainty principle was a sign that quantum mechanics was incomplete, that there must be hidden variables, underlying properties that determined the outcome of measurements, but that we had not yet been able to measure. He spent many years trying to find such hidden variables, trying to show that quantum mechanics was a statistical approximation to a deeper deterministic theory. He never succeeded. The experiments, particularly those involving Bell's theorem, have confirmed that no such hidden variables exist. The uncertainty is real. It is not an artifact of our ignorance. It is a fundamental feature of nature. The uncertainty principle has profound implications for how we think about the world. It means that there is a limit to what we can know. It means that the world is not deterministic, not in the way that classical physics envisioned. It means that randomness, or at least unpredictability, is built into the structure of reality. The future is not fully determined by the past. There is a genuine openness, a genuine indeterminacy at the heart of things. This is a hard idea to accept, but it is also a freeing one. It means that the world is not a machine, not a clockwork mechanism running according to fixed rules. It means that there is room for novelty, for the genuinely new, for the unpredictable. It means that the future is not written in advance. It is being written moment by moment through the fuzzy interactions of quantum particles, through the choices that emerge from those interactions, through the complex web of cause and effect that weaves itself through time. The uncertainty principle also has implications for the everyday world, though they are not always obvious. The principle applies to everything, not just electrons and photons. It applies to you. You have a position and a momentum, and there is a limit to how precisely both can be known. But the limit is so tiny, so absurdly small, that it has no observable effect on your daily life. For an object the size of a person, the uncertainty in position and momentum is negligible. It is far smaller than the width of an atom. It is completely swamped by the other uncertainties that affect your life, the uncertainties of weather and traffic and human relationships. The uncertainty principle is not something you need to worry about when you are walking down the street. It is something you need to worry about when you are trying to measure the position of an electron. But the fact that it applies to everything, even if the effects are too small to notice, is worth holding on to. It means that the fuzziness, the indeterminacy, the spread of possibilities is universal. It is not confined to the microscopic world. It is present everywhere. It is just hidden, buried beneath the scale of everyday life, too small to be felt but always there, always operating, always shaping the behavior of the particles that make up everything we see and touch. The uncertainty principle is one of the central pillars of quantum mechanics. It is not an add-on, it is not a minor correction. It is a direct consequence of the mathematics, of the wave-particle duality, of the deep structure of the theory. It has been tested in countless experiments, and it has never failed. It is as well established as the law of gravity, as reliable as the speed of light. Heisenberg's contribution, both the matrix mechanics and the uncertainty principle, was essential to the development of quantum mechanics. He gave physicists a mathematical framework, that was rigorous, consistent, and free of the ambiguities that plagued Bohr's model. He gave them a principle that defined the limits of what could be known. He showed that the quantum world was not a world of sharp edges and clear lines. It was a world of blur, of fuzziness, of uncertainty. As you lie there, in the quiet dark, let the uncertainty principle be something you rest in. It is not something to be feared. It is not a sign that the world is broken or that knowledge is impossible. It is a sign that the world is more flexible, more open, more creative than the classical picture allowed. It is a sign that there is room for the new, for the unexpected, for the genuine novelty that makes life worth living. The uncertainty is not a flaw, it is a feature. It is part of what makes the world interesting. It is part of what makes it worth exploring. Let the fuzziness hold you. Let the spread of possibilities be something you trust. The electrons in your body are not confined to sharp points. They are spread out, fuzzy, uncertain. They are doing what electrons do, following the rules that Heisenberg helped to formulate. Those rules are not going anywhere. They are built into the fabric of the universe, as fixed and reliable as anything we know. They have been tested and confirmed, and they have never been found wanting. You can trust them. You can rest in them. They will be there, quietly, underneath everything, holding the world together, holding you together, doing what they have always done. Rest in that. Let the uncertainty carry you into sleep. By the late 1920s, the mathematics of quantum mechanics was largely in place. Schrödinger had his wave equation, Heisenberg had his matrix mechanics and his uncertainty principle. Bohr had his model of the atom, now understood as a consequence of the wave nature of electrons. The pieces fit together. They formed a coherent framework that could be used to calculate the behavior of atoms and molecules with remarkable accuracy. But there was a problem. The mathematics worked, but nobody could agree on what it meant. The equations were clear. The predictions were accurate. But the interpretation, the story you told yourself about what was actually happening in the quantum world, was deeply contested. The central question was this: what is the wave function? Schrödinger had originally thought of it as a real physical wave, a genuine ripple in some underlying medium, like a wave on a pond. But other physicists, particularly Max Born, had proposed a different interpretation. Born suggested that the wave function was not a physical wave at all. It was a wave of probability. It described where the particle was likely to be found, not where it actually was. The particle itself was not spread out. It was just likely to be in some places and unlikely to be in others. The wave was a wave of knowledge, not a wave of matter. This interpretation, which became known as the Copenhagen interpretation after the city where Bohr worked, was developed mainly by Bohr and his colleagues. It was not a single unified theory. It was a set of principles, a way of thinking about the quantum world that emphasized the role of measurement and the limits of what could be known. The key ideas were these. First, the wave function describes the state of a system, but it does not describe a physical wave. It describes a probability distribution. Second, the act of measurement forces the wave function to collapse into a single definite outcome. Before measurement, the system exists in a superposition of all possible outcomes. After measurement, it is in one specific state. Third, there is no way to know what the system was doing before measurement. The measurement itself creates the result. This was a radical departure from classical physics. In classical physics, the world exists independently of observation. Objects have definite properties whether you measure them or not. The act of measurement does not change the object. It simply reveals what was already there. In the Copenhagen interpretation, this is not true. The act of measurement changes the system. It forces it to choose. Before measurement, the system is indefinite. After measurement, it is definite. The observer is part of the picture. The measurement is part of the process. The world is not separate from the act of looking at it. This was deeply unsettling to many physicists. Einstein, in particular, was troubled by the Copenhagen interpretation. He believed in a realistic world, a world that existed whether you looked at it or not. He believed that the wave function represented something real, something that was out there, independent of observation. He famously said that God does not play dice, meaning that the universe is not probabilistic, not a matter of chance. He wanted a deterministic theory, a theory where every particle had a definite position and momentum at all times, even if we could not know them. He spent years trying to find such a theory, trying to show that the Copenhagen interpretation was incomplete. He never succeeded. The Copenhagen interpretation became the standard view, the way most physicists were taught to think about quantum mechanics. It was not because it was obviously correct. It was because it worked. It made the right predictions. It matched the experiments. It provided a consistent framework for doing calculations. The philosophical questions, the questions about what the wave function really meant, could be set aside. They were interesting, but they were not essential. You could do physics without answering them. You could calculate the behavior of atoms and molecules without knowing what the wave function was. The equations worked, and that was enough. But the questions did not go away. They persisted, nagging, unresolved. What is a measurement? Why does it have such a special status? What happens to the wave function during collapse? Is the collapse real, or is it an illusion? These questions are still debated today. They are part of the foundations of quantum mechanics, the part that remains unsettled after nearly a century of intense study. One of the most famous challenges to the Copenhagen interpretation came from Schrödinger himself. In 1935, he proposed a thought experiment that has become legendary in the history of physics. The experiment involves a cat, a box, a radioactive atom, and a poison mechanism. The atom has a certain probability of decaying within an hour. If it decays, the poison is released and the cat dies. If it does not decay, the cat lives. According to the Copenhagen interpretation, the atom exists in a superposition of decayed and not decayed until someone opens the box and looks. But if the atom is superposed and the cat's fate is linked to the atom, then the cat must also be superposed. It must be neither definitely alive nor definitely dead. It must be both, simultaneously, until the box is opened. Schrödinger proposed this experiment not because he thought cats could be both alive and dead. He proposed it to highlight the absurdity of the Copenhagen interpretation. He wanted to show that it led to ridiculous conclusions when applied to everyday objects. He wanted to argue for a different interpretation, one that preserved the reality of the wave function and avoided the need for collapse. But the thought experiment backfired. Instead of discrediting the Copenhagen interpretation, it became a famous illustration of its strangeness. It became a symbol of the weirdness of quantum mechanics, a way of showing how different the quantum world is from the classical world. Schrödinger's cat is not a real experiment. It is a thought experiment, a way of thinking about the implications of quantum mechanics. No one has ever actually put a cat in a box with a poison mechanism. But the thought experiment is useful because it forces you to confront the strangeness of superposition. It asks you to think about what it would mean for a macroscopic object, something the size of a cat, to exist in two states at once. It asks you to think about the role of observation, about what it means to open the box and look. The Copenhagen interpretation has an answer to the cat question. It says that the cat is in a superposition until the box is opened. It says that the act of opening the box, the act of observation, forces the wave function to collapse into one definite state. But it does not explain why observation has this special status. It does not explain what counts as an observation. Is it the eye of the observer? Is it the brain? Is it the measurement device? Is it the interaction with the environment? The Copenhagen interpretation is silent on these questions. It is a pragmatic interpretation, a way of doing physics without worrying about the deep philosophical issues. It works, but it does not fully explain. This is why other interpretations have been developed. The many worlds interpretation, proposed by Hugh Everett in the 1950s, avoids the need for collapse entirely. It says that the wave function never collapses. Instead, every possible outcome actually happens, each in its own separate universe. When you open the box, the cat is alive in one universe and dead in another. You, the observer, split into two versions of yourself, one seeing a living cat and one seeing a dead cat. There is no collapse, there is only branching. The universe splits into multiple branches, each corresponding to a different possible outcome. The many worlds interpretation is elegant in its way. It removes the need for a special collapse mechanism. It treats the wave function as real, as a genuine description of what is happening. But it introduces a different kind of strangeness. It suggests that there are countless universes, countless versions of you, each experiencing a different outcome. It suggests that the universe is far larger and more complex than we ever imagined. It is a bold idea, and it has its supporters, but it is not universally accepted. It is one interpretation among many. There are other interpretations as well. The de Broglie-Bohm interpretation, also known as pilot wave theory, attempts to restore a classical picture by introducing hidden variables, underlying properties that determine the behavior of particles. It says that particles have definite positions and momentums at all times, but that they are guided by a wave, a pilot wave, that tells them where to go. This interpretation is deterministic. It avoids the randomness of the Copenhagen interpretation, but it introduces a non-local wave that acts instantaneously across space, a feature that many physicists find uncomfortable. The relational interpretation, developed by Carlo Rovelli, says that the properties of a system are not absolute, they are relative to the observer. A particle has a position relative to one observer and a momentum relative to another. There is no single objective state, there are only relationships. This interpretation is radical, but it has its advocates. The quantum Bayesian interpretation, or cubism, says that the wave function is not a description of the world. It is a description of an observer's beliefs about the world. It is a tool for updating beliefs in the light of new evidence. The wave function is in the mind of the observer, not in the world. This interpretation is deeply subjective, but it has its supporters. None of these interpretations has emerged as the clear winner. The experimental evidence is consistent with all of them. They all make the same predictions. They are all compatible with the mathematics. The choice between them is a matter of philosophy, not physics. It is a matter of which story you find most plausible, most satisfying, most compatible with your sense of how the world should be. As you lie there in the dark, let the interpretations rest. You do not need to choose one. You do not need to decide which story is correct. The mathematics works. The predictions are accurate. The experiments confirm the predictions. Whatever the wave function means, whatever happens when you open the box, the world is consistent and reliable. The electrons in your body are doing what they have always done, following the rules that have been tested and confirmed. You can trust those rules even if you do not fully understand them. You can rest in the knowledge that the world is stable, that the forces are reliable, that the quantum rules have never been known to fail. The interpretations are interesting, but they are not essential. They are stories we tell ourselves about what the mathematics means. The mathematics itself is solid. It has been tested in countless experiments, and it has never failed. That is what matters. That is what you can hold on to. The rest is speculation, beautiful speculation, fascinating speculation, but speculation nonetheless. Let it drift past you, like clouds in the night sky. Let it settle where it will. You do not need to catch it. You only need to rest. The interpretations of quantum mechanics, the debates about what the wave function meant and what happened during measurement, were fascinating and important. They touched on deep questions about the nature of reality, the role of the observer, and the limits of human knowledge. But for most physicists, these questions were secondary. The primary job of physics was to make predictions, to calculate the behavior of the physical world with accuracy and reliability. And in that regard, quantum mechanics was a resounding success. The mathematics worked. The predictions matched the experiments. The theory was coherent and consistent. But there was a problem. The mathematics of quantum mechanics, for all its power, was mostly applied to simple systems. A single electron in a hydrogen atom, a single photon passing through a slit. two particles interacting briefly. These were the systems that physicists could solve exactly. They were the systems that confirmed the theory. But the real world was not made of single electrons and single photons. It was made of vast collections of particles, trillions upon trillions of them, interacting in complex and complicated ways. The real world was messy. It was made of many-body systems, systems that could not be solved exactly, systems that required approximations and simplifications. The question was whether quantum mechanics could handle that messiness, whether it could describe the behavior of large collections of particles with the same accuracy that it described single particles. The answer, as it turned out, was yes, but the path to that answer was not straightforward. It required new concepts, new ways of thinking about the quantum world, new mathematical tools. One of the most important of these concepts was entanglement. Entanglement is a phenomenon that occurs when two or more particles interact in such a way that their wave functions become linked. Once entangled, the particles can no longer be described independently of each other. They form a single system, a single wave function that encompasses both of them. If you measure a property of one particle, the other particle's corresponding property becomes instantly determined, no matter how far apart they are. If one particle has spin up, the other has spin down. If one particle is in a particular location, the other is in a corresponding location. The correlations are perfect. They are stronger than anything that can be explained by classical physics. This is a genuinely strange phenomenon. It suggests that the particles are connected in a way that transcends space. It suggests that the universe is more interconnected than we ever imagined. It suggests that the separateness of objects, the distinctness that we take for granted, is an illusion, at least at the quantum level. At the quantum level, everything is connected. Everything is part of a single web of correlations, a single wave function that encompasses the entire universe. Einstein was deeply troubled by entanglement. He called it spooky action at a distance, a phrase that captures his discomfort. He believed that the correlations between entangled particles must be explained by some hidden information, some underlying property that the particles carried with them when they interacted. He believed that the particles were not truly connected. They were just carrying information that determined their future behavior. He spent years trying to prove this, trying to show that quantum mechanics was incomplete, that there must be hidden variables that would restore a classical picture. He never succeeded. The experiments, particularly those that tested Bell's theorem, proved that no such hidden variables exist. The correlations are real. The entanglement is real. The connection is real. Bell's theorem, proposed by the physicist John Bell in the 1960s, was a turning point. Bell showed that if hidden variables existed, they would impose certain constraints on the correlations between entangled particles. These constraints could be tested experimentally. If the experiments violated the constraints, then hidden variables were ruled out. The experiments, conducted over several decades, consistently violated the constraints. They confirmed that entanglement was real, that the correlations were stronger than any hidden variable theory could explain. The world was not classical. It was quantum. It was entangled. Entanglement has profound implications for how we think about the world. It suggests that the universe is not a collection of independent objects, each with its own properties. It suggests that the universe is a single system, a single wave function, a single web of correlations. The separateness of objects is an illusion, a consequence of the way we perceive the world, not a reflection of its underlying nature. At the deepest level, everything is connected. Everything is part of the same whole. This idea is not just philosophical. It has practical applications. Entanglement is the basis of quantum computing, a new kind of computing that uses the strange properties of quantum mechanics to perform calculations that are impossible for classical computers. Entanglement is the basis of quantum cryptography, a new kind of encryption that is theoretically unbreakable. Entanglement is the basis of quantum teleportation, a way of transferring quantum states from one place to another without physically moving the particles. These technologies are still in their early stages, but they are real. They work. They are proof that entanglement is not just a philosophical curiosity. It is a physical phenomenon that can be harnessed and used. But entanglement is also a source of confusion. It is hard to understand, hard to visualize, hard to integrate with our everyday experience. We are not used to the idea that things can be connected without being in contact. We are not used to the idea that the universe is a single system. We are used to thinking of objects as separate, distinct, independent. Entanglement challenges that way of thinking. It asks us to see the world differently, to see it as a web of relationships, a network of connections, a single, interconnected whole. As you lie there in the dark, let the idea of entanglement rest in your mind. You are not separate from the world around you. You are connected to it, entangled with it. The particles in your body have interacted with other particles, have become entangled with them, and those other particles have become entangled with still others, in a vast chain that stretches across the universe. You are part of that chain. You are part of that entanglement. You are connected to everything that has ever existed, everything that exists now, everything that will exist in the future. The connections are not visible, they are not tangible, but they are real. They are part of the fabric of the universe. This is not a mystical idea. It is a physical fact. It is a consequence of the laws of quantum mechanics, laws that have been tested and confirmed. The entanglement is real. The connections are real. The universe is a single system, a single wave function, a single web of correlations. You are part of that web. You are part of that system. You are entangled with everything around you. Let that thought be a comfort. Let it be a source of peace. You are not alone. You are not isolated. You are connected to the world in ways that go beyond what you can see or feel. The connections are there, quietly, underneath everything, holding the universe together. They have been there since the beginning of time. They will be there long after you are gone. They are part of the structure of reality, as fixed and reliable as the speed of light. Rest in that. Rest in the knowledge that you are part of something larger, something deeper, something that transcends the boundaries of space and time. The universe is connected. You are connected. And the connections will hold, as they always have, as they always will. Entanglement is one of the strangest features of quantum mechanics, but it is not the only one. There is another phenomenon, equally strange, equally counterintuitive, that has profound implications for how the universe works. It is called tunneling, and it is the reason the sun shines, the reason nuclear fusion is possible, the reason that certain chemical reactions happen at the rates they do. Tunneling is a quantum effect that allows particles to pass through barriers that they could not pass through according to classical physics. It is as if you threw a ball at a wall, and the ball appeared on the other side, without breaking the wall, without going over it, without doing anything that made sense in the ordinary world. In classical physics, a particle needs a certain amount of energy to overcome a barrier. If it does not have that energy, it bounces back. It cannot pass through. The barrier is an obstacle, a wall, a hill that is too high to climb. The particle is trapped on one side, unable to reach the other. This is intuitive. It matches everyday experience. You cannot walk through a wall. You cannot climb a hill that is too steep. You need the right amount of energy to get past an obstacle. In quantum mechanics, the rules are different. The wave function of a particle does not abruptly stop at a barrier. It decays gradually, exponentially, as it penetrates the barrier. The wave function does not vanish. It gets smaller, but it does not disappear. If the barrier is thin enough, or if the particle's wave function extends far enough, there is a non-zero probability that the particle will appear on the other side of the barrier. It does not climb over the barrier. It does not go around it. It simply appears on the other side, as if it had tunneled through. This is called quantum tunneling, and it is a real phenomenon. It has been observed in countless experiments. It is a direct consequence of the wave nature of matter. Tunneling is not a rare or exotic effect. It happens constantly, all around you, inside you. It is responsible for the fusion of hydrogen nuclei in the sun. The sun's core is extremely hot and dense, but it is not hot enough, by classical standards, to fuse hydrogen into helium. The hydrogen nuclei, which are positively charged, repel each other. They need a lot of energy to overcome this repulsion and get close enough to fuse. The temperature of the sun's core provides some of that energy, but not all of it. If classical physics were the whole story, the sun would not shine. It would be a cold, dead ball of gas. But the sun does shine, because quantum tunneling allows a small fraction of the hydrogen nuclei to fuse despite the repulsion. The tunneling probability is small, but the sun is large. There are so many nuclei that even a tiny probability produces a vast number of fusion events. The energy released by these events powers the sun, and that energy, in turn, powers almost everything on Earth. Tunneling is also responsible for the decay of radioactive nuclei. Some nuclei are unstable. They emit particles and transform into more stable configurations. This decay process is governed by quantum tunneling. The particles inside the nucleus are trapped by a barrier, the strong nuclear force, which holds the nucleus together. But the particles also have a wave function that extends beyond the barrier. There is a small probability that they will appear outside the nucleus, and when they do, they are emitted. The decay rate is determined by the probability of tunneling. This is why some radioactive isotopes have half-lives of billions of years, while others decay in fractions of a second. The barrier height and width determine the tunneling probability, and the tunneling probability determines the decay rate. Tunneling is also important in chemistry. Many chemical reactions proceed at rates that cannot be explained by classical physics alone. The reactants need to overcome an energy barrier to form products. Sometimes they do not have enough energy to climb over the barrier, but they react anyway. This is because quantum tunneling allows them to pass through the barrier rather than over it. The tunneling rate depends on the shape of the barrier, and it can be significant for reactions involving light particles, like electrons and protons. Tunneling is a key factor in enzyme catalysis, in the chemistry of photosynthesis, in the behavior of molecules at low temperatures. It is everywhere in chemistry, quietly enabling reactions that would otherwise be impossible. Tunneling is also the basis of a number of technologies. The Scanning Tunneling Microscope, or STM, uses tunneling to image surfaces at the atomic scale. A sharp metal tip is brought very close to a surface, but not touching it. A voltage is applied, and electrons tunnel across the gap between the tip and the surface. The tunneling current is extremely sensitive to the distance between the tip and the surface. By scanning the tip across the surface and measuring the current, the STM can produce images of individual atoms. It can show you the arrangement of atoms on a surface, the defects, the impurities, the details that are invisible to ordinary microscopes. The STM is a direct application of quantum tunneling, a way of using the quantum world to see the quantum world. Tunneling is also important in electronics. The tunnel diode, for example, uses tunneling to achieve switching speeds that are much faster than conventional diodes. The tunnel field effect transistor, or TFET, uses tunneling to achieve lower power consumption than conventional transistors. These devices are still in development, but they show the potential of tunneling for future electronics. Tunneling is not just a curiosity, it is a tool, a resource, a way of doing things that is not possible in the classical world. The phenomenon of tunneling is a direct consequence of the wave nature of matter. It is a reminder that the quantum world is not like the classical world. It is a reminder that the rules are different, that the barriers are not absolute, that the impossible is sometimes possible. Tunneling is a strange phenomenon, but it is also a beautiful one. It shows the flexibility of the quantum world, the fluidity of the quantum rules, the way that the universe can surprise you with what it allows. As you lie there, in the quiet dark, let the idea of tunneling rest in your mind. Think about the barriers that seem absolute, the walls that seem impenetrable. In the quantum world, those barriers are not absolute. They are fuzzy, permeable, open to the possibility of passage. The universe is not rigid, it is not fixed. It is flexible, fluid, open to the improbable, the unlikely, the seemingly impossible. The sun shines because of tunneling. The stars burn because of tunneling. The elements that make up your body were forged in stars, through tunneling. You are made of tunneling. You are a product of the quantum world. The barriers in your own life, the walls that seem insurmountable, the obstacles that seem impossible to overcome, they are not absolute either. They are not fixed. They are not permanent. They are open to the possibility of passage, the possibility of change, the possibility of something new. Tunneling is a reminder that the universe is not deterministic, not fixed, not closed. It is open, flexible, full of possibilities. The improbable happens, the unlikely occurs, the impossible becomes possible. That is the nature of the quantum world, and that is the nature of the universe we live in. Rest in that. Rest in the possibility. Rest in the openness. The walls are not as solid as they seem. The barriers are not as absolute as they appear. There is always a way through, a way around, a way past. The universe is full of surprises, full of possibilities, full of the unexpected. Tunneling is a reminder of that. It is a reminder that the quantum world is not a prison. It is a playground, a field of infinite possibility, a place where the rules are flexible and the outcomes are not predetermined. The future is not fixed. It is open. It is waiting to be shaped by the choices you make, the actions you take, the paths you choose. Tunneling is a metaphor for that openness, that flexibility, that possibility. The electrons in your body are tunneling through barriers right now, quietly, continuously, doing what electrons do. They are not trapped. They are not confined. They are moving, flowing, passing through walls that should not be passable. They are doing what they have always done, following the rules that have been written into the universe since the beginning of time. Those rules are not rules of confinement. They are rules of possibility, rules of openness, rules of the unexpected. The universe is not a machine. It is a living, breathing, evolving thing, full of surprises, full of possibilities, full of the unexpected. Tunneling is a reminder of that. Rest in that. Rest in the openness. Rest in the possibility. The future is not fixed. It is waiting for you. Tunneling is strange, but it is not the strangest thing quantum mechanics has to offer. There is another property of particles, a property that seems almost impossible to believe, that has been confirmed by countless experiments and is now a standard part of the theory. This property is called spin, and it is one of the most fundamental properties of matter. Every electron has spin, every proton has spin, every neutron has spin. Spin is a form of angular momentum, a kind of built-in rotation, but it is not rotation in the ordinary sense. It is an intrinsic property, a property that a particle has simply by existing, like mass or electric charge. It does not come from the particle spinning around an axis, the way a planet spins. It is something deeper, something more fundamental, something that is part of the particle's identity. The concept of spin was introduced in the mid-1920s, when physicists were trying to understand the behavior of electrons in atoms. They had noticed that certain spectral lines, the barcode lines that Bohr's model explained so well, were not single lines. They were doublets, pairs of lines that were very close together but not identical. Something was splitting the lines, creating a subtle structure that the existing theories could not explain. The physicist Wolfgang Pauli proposed a solution. He suggested that electrons had an additional property, a two-valued property, that could take one of two values. He called this property spin, and he said it could be up or down. The spin of an electron could be aligned with a magnetic field or against it. There were no other options. Spin was binary, like a switch that could be on or off. This was a bold proposal, and it was initially met with skepticism. Spin seemed too abstract, too mathematical, too disconnected from physical reality. But the evidence soon accumulated. The splitting of spectral lines was explained perfectly by spin. The behavior of electrons in magnetic fields was explained perfectly by spin. The structure of atoms, the periodic table, the chemical properties of elements, all of them depended on spin. Spin was not a mathematical fiction, it was a physical property of electrons, as real as their charge or their mass. But spin was also deeply strange. It did not behave like ordinary angular momentum. If you have a spinning top, you can change its spin by applying a force. You can make it spin faster or slower. You can change the direction of its spin. With an electron, it is different. The spin of an electron is fixed. It has a single magnitude, a single value that cannot be changed. You can change the direction of the spin, but you cannot change its magnitude. It is always the same. And when you measure the spin of an electron along a particular axis, you always get one of two values, up or down. There is no in-between. The spin is quantized, just like energy. This quantization is one of the most important features of spin. It means that spin is not a continuous quantity. It is discrete, like the rungs on Bohr's ladder. There are only two possible values for an electron's spin along any given axis. This discreteness is what makes spin so useful in quantum mechanics. It provides a simple binary description of particles, a way of encoding information in a quantum system. This is the basis of quantum computing, where the spin of an electron can represent a bit of information, a 0 or a 1. The spin can be in a superposition of up and down, allowing for computations that are impossible in classical computers. Spin is also responsible for one of the most fundamental rules of nature, the Pauli exclusion principle. Wolfgang Pauli, the same physicist who introduced spin, formulated the principle in 1925. It states that no two electrons in an atom can occupy the same quantum state. They cannot have the same set of quantum numbers, the same energy level, the same orbital shape, and the same spin. The exclusion principle applies to fermions, a class of particles that includes electrons, protons, and neutrons. It does not apply to bosons, another class of particles that includes photons. The exclusion principle is one of the most important principles in physics. It is the reason atoms have structure. It is the reason electrons occupy distinct shells around the nucleus, rather than all collapsing into the lowest energy state. It is the reason matter is stable, the reason you do not fall through the floor, the reason the world has the solidity it has. Without the exclusion principle, all matter would collapse into a dense, compact clump. Atoms would not exist. Molecules would not exist. Chemistry would not exist. Life would not exist. The exclusion principle is a fundamental rule of the universe, and it is directly tied to the spin of electrons. The exclusion principle also explains the periodic table of elements. The periodic table is a chart of the elements, arranged by their chemical properties. It is one of the most elegant and useful tools in chemistry. It organizes the elements into rows and columns, with similar elements in the same column. The structure of the periodic table is a direct consequence of the exclusion principle. The electrons in an atom fill the available quantum states, starting from the lowest energy and moving upward. Each state can hold two electrons, one with spin up and one with spin down. The shells fill in a specific order, and the number of electrons in the outermost shell determines the chemical properties of the element. The periodic table is a map of the exclusion principle, a visual representation of the quantum structure of atoms. Spin is also important in magnetic resonance imaging, or MRI. MRI is a medical imaging technique that uses magnetic fields and radio waves to create detailed images of the inside of the body. It works by exploiting the spin of protons, particularly the protons in hydrogen atoms. Hydrogen is abundant in the body, in water and fat. The protons in these hydrogen atoms have spin, and they act like tiny magnets. When you put a patient in a strong magnetic field, the spins of the protons align with the field. Then you apply a pulse of radio waves, which tips the spins out of alignment. As the spins relax back into alignment, they emit radio signals that can be detected and used to create an image. MRI is a direct application of quantum spin, a way of using the quantum properties of matter to see inside the body. Spin is a fundamental property of matter, a property that has no classical analog. It is not something you can touch or feel or see. It is not something you can visualize in ordinary terms. It is a quantum property, a property of the quantum world, a property that exists only at the smallest scales. But it is real. It has measurable effects. It shapes the behavior of atoms and molecules. It determines the structure of matter. It is the basis of technologies that are used every day. Spin is not an abstract concept. It is a physical reality. As you lie there in the quiet dark, let the idea of spin rest in your mind. Think about the electrons in your body, each one carrying its own spin, up or down. Think about the exclusion principle, the rule that keeps those electrons from occupying the same state, the rule that gives atoms their structure. Think about the periodic table, the elegant map of the quantum world, the chart that organizes all the elements. Think about MRI, the technology that uses spin to see inside the body, to diagnose disease, to save lives. Spin is everywhere. It is in your body. It is in the world around you. It is part of the fabric of the universe. Spin is also a reminder of the strangeness of the quantum world. It is a property that does not fit into our everyday experience. It is not something we can see or touch or feel. It is something we can only understand through mathematics, through the language of quantum mechanics. That is one of the most profound lessons of quantum mechanics. The world is not what it appears to be. It is not intuitive. It is not easy to understand. It is strange, unfamiliar, and full of surprises. But it is also beautiful, elegant, and deeply coherent. The quantum world is a world of rules, a world of principles, a world of order. And spin is one of those rules, one of those principles, one of those pieces of order. Rest in that order. Rest in the rules that govern the universe. Rest in the knowledge that the spin of electrons, the exclusion principle, the structure of atoms, the periodic table, the MRI machine, all of these are part of a single coherent picture. They are all connected. They are all part of the same story, the story of quantum mechanics. It is a story that began with a hot oven and a color problem, and it continues to unfold today. It is a story that is still being written, still being explored, still being understood. And you are part of that story. You are made of the same particles that physicists study. You are governed by the same rules. You are a quantum object, as much as any electron or atom. The rules apply to you, even if you cannot feel them. They are there, quietly, underneath everything, holding you together, keeping you stable, keeping you whole. Rest in that. Rest in the quantum world. Rest in the strange, beautiful, coherent order of the universe. The story of quantum mechanics, as it has unfolded over the course of this night, has been a story of gradual revelation. It began with a simple observation, the glow of a hot object, and it has led to a description of the world that is strange and beautiful and deeply counterintuitive. It has shown us that energy comes in discrete packets, that light is both a wave and a particle, that matter is also a wave, that the universe is probabilistic rather than deterministic, that particles can be entangled across vast distances, that they can tunnel through barriers that should be impenetrable, and that they carry an intrinsic property called spin that determines much of their behavior. It has shown us that the solid world of everyday experience is an illusion, a consequence of the quantum rules that govern the behavior of electrons and atoms. It has shown us that the universe is not a machine, not a clockwork mechanism, but a living, breathing, evolving thing, full of surprises and possibilities. But the story is not over. It is still being written. There are questions that remain unanswered, puzzles that remain unsolved, mysteries that remain unexplored. One of the most profound of these mysteries is the nature of the wave function itself. What is it? Is it a real physical wave, a ripple in some underlying medium, or is it a mathematical abstraction, a tool for calculating probabilities? The Copenhagen interpretation, which has been the dominant view for most of the history of quantum mechanics, treats the wave function as a wave of probability. It says that the wave function does not represent a physical wave. It represents the probability of finding the particle in a particular location. The particle itself is not spread out. It is just likely to be in some places and unlikely to be in others. The wave is a wave of knowledge, not a wave of matter. But there are other interpretations. The many worlds interpretation, proposed by Hugh Everett in the 1950s, treats the wave function as real. It says that the wave function never collapses. Instead, every possible outcome actually happens, each in its own separate universe. The universe splits into multiple branches, each corresponding to a different possible outcome. The cat is alive in one universe and dead in another. You, the observer, split into multiple versions of yourself, each experiencing a different outcome. There is no collapse, there is only branching. The wave function is real. It describes the entire multiverse, the vast collection of all possible universes. The many worlds interpretation is elegant in its way. It removes the need for a special collapse mechanism. It treats the wave function as a complete description of reality. But it introduces a different kind of strangeness. It suggests that there are countless universes, countless versions of you, each experiencing a different outcome. It suggests that the universe is far larger and more complex than we ever imagined. It is a bold idea, and it has its supporters, but it is not universally accepted. It is one interpretation among many. Another interpretation is the de Broglie-Bohm interpretation, also known as pilot wave theory. This interpretation, proposed by Louis de Broglie and later developed by David Bohm, attempts to restore a classical picture by introducing hidden variables. It says that particles have definite positions and momentums at all times, but that they are guided by a wave, a pilot wave, that tells them where to go. The pilot wave is a real physical wave, not a wave of probability. It determines the behavior of the particles. The particles themselves are like ships on an ocean, guided by the waves. The pilot wave is the wave function. It is real. It is physical. It exists. The de Broglie-Bohm interpretation is deterministic. It avoids the randomness of the Copenhagen interpretation. But it introduces a non-local wave that acts instantaneously across space, a feature that many physicists find uncomfortable. It also requires the introduction of hidden variables, properties that are not directly observable. This violates the spirit of quantum mechanics, which is a theory of observables. But it is a consistent interpretation, and it makes the same predictions as the Copenhagen interpretation. It is a viable alternative. There are other interpretations as well. The relational interpretation, developed by Carlo Rovelli, says that the properties of a system are not absolute. They are relative to the observer. A particle has a position relative to one observer and a momentum relative to another. There is no single objective state. There are only relationships. This interpretation is radical, but it has its advocates. The quantum Bayesian interpretation, or cubism, says that the wave function is not a description of the world. It is a description of an observer's beliefs about the world. It is a tool for updating beliefs in the light of new evidence. The wave function is in the mind of the observer, not in the world. This interpretation is deeply subjective, but it has its supporters. None of these interpretations has emerged as the clear winner. The experimental evidence is consistent with all of them. They all make the same predictions. They are all compatible with the mathematics. The choice between them is a matter of philosophy, not physics. It is a matter of which story you find most plausible, most satisfying, most compatible with your sense of how the world should be. This is a remarkable situation. After nearly a century of intense study, the foundations of quantum mechanics remain unsettled. The mathematics is solid, the predictions are accurate, but the interpretation, the meaning, remains open. This openness is not a weakness. It is a strength. It shows that quantum mechanics is a living theory, a theory that is still being explored, still being understood. It shows that the questions are deep, that they touch on the nature of reality, on the role of the observer, on the limits of human knowledge. These are questions that have occupied philosophers for millennia. They are questions that are now being addressed by physics. They are questions that may never be fully answered, but that is not a reason to stop asking them. The asking is part of the process. The asking is part of the journey. As you lie there in the quiet dark, Let the openness of quantum mechanics be something you rest in. The questions are not a sign of failure, they are a sign of vitality. They are a sign that the theory is alive, that it is still growing, that it is still reaching toward deeper understanding. The universe is not a closed book. It is an open one. There are pages that have not been written yet, chapters that have not been explored, mysteries that have not been solved. That is the nature of science. That is the nature of human inquiry. We do not have all the answers. We may never have all the answers, but we keep asking, we keep exploring, we keep reaching. The wave function, whatever it is a description of the quantum world. It is a description that has been tested and confirmed. It is a description that works. The interpretations are stories we tell ourselves about what the description means. They are important, but they are not essential. The description is essential. The description is what we use to make predictions, to build technologies, to understand the world. The interpretation is what we use to make sense of it all, to fit it into our larger worldview. Both are valuable. Both are part of the process. Rest in that process. Rest in the journey. Rest in the knowledge that the questions are not a problem. They are an invitation. They are an invitation to think, to explore, to wonder. The universe is full of wonder. It is full of mystery. It is full of beauty. And quantum mechanics is one of the most beautiful parts of it. It is a theory that shows us the world in a new light, a light that is strange and unfamiliar, but also deeply coherent. It is a theory that challenges our assumptions, expands our minds, and opens us up to new possibilities. It is a theory that invites us to rest in the mystery, to let go of the need for certainty, and to embrace the unknown. Rest in that. Let the mystery hold you. Let the questions carry you into sleep. The interpretations of quantum mechanics, the debates about what the wave function means, the questions about the role of the observer and the nature of reality, these are the deep puzzles that occupy the minds of physicists and philosophers. But for most people, the practical applications of quantum mechanics are more immediate. They are the technologies that shape everyday life, the devices that have become so familiar that they are almost invisible. And these technologies are everywhere. They are in the room with you right now, quietly doing their work, making modern life possible. Consider the device that might be resting on your nightstand, or on the table beside your bed, or even in your hand. That device, whatever it is a direct descendant of the quantum revolution. It contains a microprocessor, a chip that is made of billions of transistors. Each transistor is a tiny switch, a device that can be on or off, representing a 1 or a 0. These transistors are the building blocks of digital information. They are the reason your device can compute, can store data, can connect to the internet. And they work because of quantum mechanics. A transistor is a semiconductor device. It is made of materials like silicon, which have a special property. They can conduct electricity, but not as well as metals. They are somewhere in between. The conductivity of a semiconductor is determined by the behavior of its electrons, and that behavior is governed by quantum mechanics. The electrons in a semiconductor occupy specific energy bands, separated by gaps. The bands are a direct consequence of the wave nature of electrons, of the quantum rules that govern their behavior. The gaps are the same kind of gaps that Bohr observed in the hydrogen atom, the rungs on the ladder. The transistor works by controlling the flow of electrons across these gaps. It is a quantum device, built on quantum principles. The transistor was invented in 1947 by a team of physicists at Bell Laboratories. It was a breakthrough. It replaced the vacuum tube, which was bulky, fragile, and power-hungry. The transistor was small, reliable, and efficient. It was the beginning of the digital age. Since then, transistors have gotten smaller and smaller. They are now measured in nanometers, billionths of a meter. There are billions of them on a single chip. They are so small that quantum effects are not just important, they are dominant. The transistor is a quantum device, through and through. It is the foundation of modern electronics. But the transistor is not the only quantum technology. There is also the laser. The laser is a device that produces a beam of coherent light that is all the same frequency and all in phase. It is used in everything from barcode readers to surgical tools to telecommunications. The laser works because of a quantum phenomenon called stimulated emission. This phenomenon was first predicted by Einstein in 1917, long before anyone had built a laser. He showed that if you had a collection of atoms, you could stimulate them to emit light in a particular direction. The light would be coherent, all the same frequency, all in phase. This was a purely quantum prediction. It was a consequence of the quantum rules that govern the behavior of atoms, and it turned out to be correct. The laser was built in 1960, and it has been a cornerstone of technology ever since. Another quantum technology is the light-emitting diode, or LED. An LED is a device that emits light when a current passes through it. It is used in everything from indicator lights to television screens to room lighting. The LED works because of the same quantum principles that govern the transistor. The electrons in the LED occupy specific energy bands. When they drop from a higher band to a lower band, they emit a photon of light. The color of the light is determined by the size of the gap between the bands. The gap is a quantum property, a consequence of the wave nature of electrons. The LED is a quantum device, built on quantum principles. Another quantum technology is the MRI machine. MRI, or magnetic resonance imaging, is a medical imaging technique that uses magnetic fields and radio waves to create detailed images of the inside of the body. It works by exploiting the spin of protons, particularly the protons in hydrogen atoms. The protons are like tiny magnets, and they align with a strong magnetic field. Then a pulse of radio waves tips them out of alignment. As they relax back into alignment, they emit radio signals that can be detected and used to create an image. The spin of the proton is a quantum property. It is a consequence of the quantum rules that govern the behavior of particles. The MRI machine is a quantum device, built on quantum principles. There are other quantum technologies as well. The atomic clock, which is used in GPS satellites, relies on the quantum behavior of atoms. The electron microscope, which can image individual atoms, relies on the wave nature of electrons. The solar cell, which converts sunlight into electricity, relies on the quantum behavior of electrons in semiconductors. The list goes on. Quantum mechanics is not just a theory. It is a toolbox. It is a set of principles that can be used to build devices that do things that were previously impossible. The technologies are so pervasive that it is easy to forget they are quantum. They are just part of the background, part of the modern world. But they are a testament to the power of quantum mechanics. They are proof that the theory works, that it is not just a collection of abstract ideas, but a practical tool for shaping the world. They are proof that the quantum world is not separate from the everyday world. It is the everyday world. It is the world we live in. As you lie there in the quiet dark, let the quantum technologies be something you rest in. The device on your nightstand, the lights in the room, the clock on the wall, the MRI machine at the hospital, the GPS satellite in orbit, all of them are quantum. All of them are built on the same principles that were discovered by Planck and Einstein and Bohr and the others. They are proof that the quantum rules are real, that they are reliable, that they can be trusted. They have been tested and confirmed, and they have never failed. They are the foundation of the modern world. They are holding you up, holding you together, keeping you connected to the world around you. Rest in that. Let the quantum technologies be a comfort, a reminder that the world is stable, that the rules are reliable, that the future is open. The devices will continue to work, quietly, continuously, doing what they do. You can trust them, you can rest in them. They will be there, as they always have been, as they always will be. The quantum technologies that surround you, the transistors and lasers and LEDs and MRI machines, are proof that quantum mechanics works. They are proof that the theory is not just a collection of abstract ideas, but a practical tool for shaping the world. But there is another layer to the story. a layer that connects the quantum world to the largest structures in the universe, to the stars and the galaxies, and the very fabric of space and time. This layer involves the quantum origins of the universe itself, the way that quantum fluctuations in the early cosmos gave rise to the structures we see today. It is a story that begins at the smallest scales and ends at the largest, a story that connects the quantum world to the cosmos. The universe began about 13.8 billion years ago in an event called the Big Bang. At the very beginning, the universe was unimaginably hot and dense. It was a soup of particles and radiation, a chaotic sea of energy. The rules that governed this early universe were quantum rules. The particles were governed by quantum mechanics. The fields were governed by quantum field theory. The entire universe was a quantum object, a vast wave function evolving according to the Schrödinger equation. The quantum world was not a small corner of the universe. It was the whole universe. As the universe expanded and cooled, it underwent a series of phase transitions. These transitions were driven by quantum effects, by the behavior of particles and fields at the smallest scales. One of the most important of these transitions was inflation, a period of rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation was driven by a quantum field, a field that had a particular energy density. The field fluctuated, as quantum fields do, and these fluctuations were amplified by the rapid expansion. They became the seeds of structure, the tiny variations in density that would eventually grow into galaxies and clusters of galaxies. The fluctuations were quantum in origin. They were the result of the uncertainty principle, of the inherent fuzziness of the quantum world. They were random, unpredictable, probabilistic. They were a direct manifestation of the quantum rules that govern the behavior of fields. And they left their imprint on the cosmic microwave background, the afterglow of the Big Bang. The cosmic microwave background is a faint glow of radiation that fills the universe. It is the oldest light in the universe, a relic from the time when the universe first became transparent. And it contains tiny variations in temperature, variations that correspond to the quantum fluctuations that occurred during inflation. The patterns in the cosmic microwave background are a direct image of the quantum world, a snapshot of the universe when it was a fraction of a second old. The quantum fluctuations that seeded the galaxies are a profound connection between the very small and the very large. They show that the universe is not a machine. It is not deterministic. It is probabilistic, random, open. The structures we see around us, the galaxies, the stars, the planets, all of them are the result of quantum fluctuations, of the inherent uncertainty of the quantum world. The universe is not a clockwork mechanism. It is a quantum object, a wave function that has evolved over billions of years. This connection between the quantum world and the cosmos is one of the most beautiful insights of modern physics. It shows that the rules that govern the behavior of atoms and electrons are the same rules that govern the behavior of the universe as a whole. It shows that the quantum world is not a separate world. It is the foundation of everything. It is the bedrock on which the entire universe is built. The quantum origins of the universe also raise profound questions about the nature of time and space. In the early universe, the quantum fluctuations were so large that they may have affected the very fabric of space and time. Space and time are not absolute. They are flexible, dynamic, subject to quantum effects. The quantum fluctuations may have caused space and time to ripple, to curve, to bend. These ripples, called gravitational waves, have been detected by experiments like LIGO. They are a direct probe of the quantum world, a way of seeing the effects of quantum gravity. Quantum gravity is one of the great unsolved problems in physics. It is the attempt to unify quantum mechanics and general relativity, the theory of gravity. General relativity describes gravity as the curvature of space and time. Quantum mechanics describes the behavior of particles and fields. They are both successful theories, but they are incompatible. They cannot both be true at the same time, in the same place. A quantum theory of gravity would be a theory that unifies them, that describes the behavior of space and time at the smallest scales. It would be a theory of quantum space-time, a theory of the quantum origins of the universe. There are several approaches to quantum gravity. One is string theory, which proposes that the fundamental building blocks of the universe are not particles but strings, tiny one-dimensional objects that vibrate at different frequencies. The vibrations correspond to different particles. String theory is a bold idea, and it has made progress in several areas, but it is still incomplete. It has not yet made predictions that can be tested experimentally. Another approach is loop quantum gravity, which proposes that space and time are not continuous but discrete, made of tiny loops. This approach is also incomplete. It has not yet made predictions that can be tested. The search for a quantum theory of gravity is one of the great challenges of modern physics. The quantum origins of the universe are a reminder that the quantum world is not just about atoms and electrons. It is about everything. It is about the beginning of time, the structure of space, the nature of reality. The quantum rules are universal. They apply to everything, from the smallest particle to the largest galaxy. They are the rules of the universe, the laws of physics. They are not arbitrary. They are not imposed from outside. They are the way the universe works. As you lie there in the quiet dark, let the quantum universe be something you rest in. The universe is a quantum object, a vast wave function evolving according to the Schrödinger equation. It is probabilistic, open, full of possibilities. It is not a machine. It is a living, breathing, evolving thing. It is a universe that is still being created, still unfolding, still becoming. The quantum fluctuations that seeded the galaxies are still happening, still shaping the universe, still creating new structures. The universe is not finished. It is still being written. You are part of that universe. You are made of the same stuff as the stars. You are governed by the same rules. You are a quantum object, a wave function, a bundle of possibilities. The quantum world is not separate from you. It is you. The rules that govern the behavior of atoms and electrons are the rules that govern your behavior, the behavior of your body, the behavior of your mind. The quantum world is not a foreign land. It is your home. It is the world you live in. Rest in that. Rest in the quantum universe. Rest in the knowledge that you are connected to everything, that you are part of the cosmic web, that the quantum fluctuations that seeded the galaxies are also part of you. The universe is not a cold, empty place. It is a living, breathing, evolving thing, full of possibilities, full of surprises, full of beauty. And you are part of that beauty. You are part of that possibility. You are part of the quantum universe. Rest in that. Let the quantum universe carry you into sleep. And so, as the night deepens around you and the weight of your body settles further into the mattress, it is worth pausing to consider where this journey has taken you. It began with a simple question, a puzzle about the glow of a hot object, a small crack in the wall of classical physics that seemed too minor to matter. But that crack widened, and through it poured a new understanding of the world, a vision of reality that was stranger and more beautiful than anyone could have imagined. You have traveled through the history of quantum mechanics, from Planck's reluctant quanta to Einstein's photons, from Bohr's rungs to de Broglie's waves, from Schrödinger's equation to Heisenberg's uncertainty, from the probabilistic interpretation to the mysteries of entanglement and tunneling. You have seen how these ideas, abstract and counterintuitive as they are, have given rise to the technologies that define modern life, from transistors to lasers to MRI machines. And you have glimpsed the quantum origins of the universe itself, the way that fluctuations at the smallest scales have shaped the largest structures in the cosmos. This journey has been long, but it has not been a journey you needed to follow step by step. It has been a journey you could drift through, letting the ideas wash over you like waves, letting the words carry you towards sleep. And now, as you approach the end of this journey, it is worth asking what it all means. Not in a technical sense, not in terms of equations or experiments, but in a deeper sense. What does quantum mechanics tell us about the nature of reality, about our place in the universe, about the way we should live our lives. The first lesson of quantum mechanics is that the world is not what it appears to be. It is not solid, not continuous, not deterministic. It is fuzzy, probabilistic, full of possibilities. The solidity of the bed beneath you, the stability of the room around you, these are illusions, emergent properties that arise from the quantum behavior of atoms and electrons. The world is not a machine, it is a quantum object, a wave function, a bundle of possibilities. The future is not fixed, it is open, waiting to be shaped. The second lesson is that the universe is interconnected. Entanglement shows that particles can be linked across vast distances, that the separateness of objects is an illusion. The universe is a single system, a single wave function, a single web of correlations. You are not separate from the world around you. You are connected to it, entangled with it. The particles in your body have interacted with other particles, have become entangled with them, and those other particles have become entangled with still others, in a vast chain that stretches across the universe. You are part of that chain. You are part of that entanglement. You are connected to everything that has ever existed, everything that exists now, everything that will exist in the future. The third lesson is that the universe is not deterministic. It is probabilistic, random, open. The uncertainty principle shows that there is a fundamental limit to what can be known, a limit that is built into the structure of reality. The future is not written in advance. It is being written moment by moment through the interactions of quantum particles, through the choices that emerge from those interactions, through the complex web of cause and effect that weaves itself through time. The universe is not a clockwork mechanism. It is a living, breathing, evolving thing, full of surprises, full of possibilities. The fourth lesson is that the quantum world is not separate from the everyday world. It is the everyday world. The rules that govern the behavior of atoms and electrons are the rules that govern the behavior of everything. They are universal. They apply to you, to your body, to your mind. You are a quantum object, a wave function, a bundle of possibilities. The quantum world is not a foreign land. It is your home. It is the world you live in. The fifth lesson is that the quantum world is a source of wonder. It is strange, counterintuitive, full of surprises. It challenges our assumptions, expands our minds, opens us up to new possibilities. It invites us to question, to explore, to wonder. It reminds us that the universe is not a closed book. It is an open one. There are pages that have not been written yet, chapters that have not been explored, mysteries that have not been solved. The questions are not a sign of failure. They are a sign of vitality. They are a sign that the universe is alive, that it is still growing, that it is still reaching toward deeper understanding. As you lie there in the quiet dark, let these lessons settle into your mind. Let them be a comfort, a source of peace, a reminder that the world is not a cold, empty place. It is a living, breathing, evolving thing, full of possibilities, full of surprises, full of beauty. You are part of that beauty. You are part of that possibility. You are part of the quantum universe. The quantum rules are not arbitrary. They are the way the universe works. They have been tested and confirmed. They have never failed. You can trust them. You can rest in them. They will be there quietly underneath everything, holding the world together, holding you together, doing what they have always done. The night is yours. The darkness is yours. The quiet is yours. Let it wrap around you, soft and warm, like a blanket. Let it carry you down, into the depths of sleep, into the world of dreams. The quantum world will still be here when you wake. The electrons will still be spinning. The photons will still be traveling. The wave functions will still be evolving. The universe will still be unfolding, moment by moment, in all its strange and beautiful complexity. But you do not need to be awake for it. You do not need to be aware. The universe does not require your attention. It was doing this before you were born. It will be doing this long after you are gone. It will keep doing what it does, quietly, continuously, reliably, as it always has. So let go. Let go of the thoughts, the worries, the questions. They will still be there tomorrow, if you want them. But tonight, they can rest. You can rest. The bed is soft, the room is warm, the night is quiet. Let your breathing slow, let your muscles relax, let your mind drift. There is nothing you need to do. There is nothing you need to fix. The universe is handling itself as it always has, as it always will. And you are part of that handling. You are part of that flow. You are part of that unfolding. Let it carry you, like a wave, into the depths of sleep. Let it hold you, like a field, in its gentle embrace. Let it rest you, like a quantum, in its stable, reliable state. Rest now. The rest of the night is yours. The darkness is yours. The peace is yours. Let it all go. Let yourself go. Let the quantum world carry you into sleep.